flux has moved. Our intuition tells us that it should be 0 everywhere except at that edge. Okay. So another example, let's say they were separated that way. It's the same, essentially. Maybe your cadence was not very good and the dipole has already separated, or that's the one polarity has moved further. But it's the same thing. But again, our intuition tells us that, oh, the electric field should be just there, at those two edges, okay? Or if you have a limited field of view, and then something came in, or there's some positive flux, change of flux. Again, it's the same. But in this case, the electric field is non-zero at the edge. Okay. All right. So why do we have this intuition? Well, we have this intuition about compact electric fields because, let's see. Okay, let's see. Because in MHD, the electric field we think of is a phi cross B or a curl of J. So it's linear in B. We tend to think of it that way. When B is 0, we tend to think the electric field should be 0. That's just how we think in MHD. In an electrostatic problem, that's different. So just from the pure physical intuition that electric fields should be compact except where magnetic fields are, we want to solve for a solution of the electric field that is compact in space. Okay? And you can write this as a matrix equation, and it would be an underdetermined system if you have just a running difference vertical magnetogram, and you're solving for almost 2 times, more than 2 times the number of quantities. But the fact that we want to solve for a compact electric field means that we can encode it in mathematics by minimizing the L1 norm, which is the absolute sum, or the sum of the absolute components of electric field. So that's an optimization problem. Okay. Yes, okay, I already covered this. That's an optimization problem, and Yates basically introduced this method of trying to find compact electric fields, okay? And when you do that, it's similar to basically solving a 15 puzzle, but you're trying to minimize the amount of flux that is transported between pixels in order to explain the running difference magnetogram. Anyway, so minimizing the L1 norm gives you an electric field, which this is from solving that equation, minimizing that equation. It basically gives you the electric field that is consistent with your intuition. Okay. So this electric field tells you how flux is moving around. And actually, for the magnetograms that we have from the Sun-Earth line, we don't see the entire 4 pi steradian of the sun, and sometimes we have positive or leading polarities that rotate into our field of view. But nevertheless, we want to update our surface flux transport model. And if we just introduce those polarities as a source in our magnetograms, we might run into divergence errors. But when you solve for an electric field that is compact, you can actually get around that problem, and you can update your surface flux transport model in a way that keeps local flux balance and allows you to ingest the data directly. So that's one example of machine learning. Well, it doesn't feel like it's very far from flare prediction when people talk about machine learning for solar physics. But it is essentially the same thing, that you're trying to do an optimization problem inspired by some physical intuitions and equations. So another case study is thermodiagnostics with AIA. So we have these images from AIA, but each one is actually due to plasma, possibly due to plasma at different temperatures. Each has a temperature response function that is not a delta function in log T, and we're trying to disentangle the multi-thermal nature of the filters from the multi-thermal nature of the plasma in the corona. And then you can set up something like that. Again, okay, fine. You can set up, again, a matrix equation. And this is an underdetermined system again. And you can do the same trick. You minimize the L1 norm of the emission measure to explain your signal. And then you can produce temperature maps that look like this. So these are emission measure maps for an active region, which would be consistent with what's with different scans of ice lines at different temperatures. And if you want to learn how to do the DEM analysis this way, there is a tutorial at tinyurl.com/ADEM. Okay, right. So that's another machine learning application. We know that the DEMs work quite well because when you fold the temperature, the DEMs with the XRT temperature response functions, the synthetic XRT images actually look like the real XRT images. So these two rows are for different filters in XRT. So that tells us that this inversion method works quite well. But you can take it beyond that. So that method does about 8,000 pixels or 10,000 pixels per second. It's good enough to do DEM maps. But can we train a neural network to actually do the DEM even faster? And the answer is we can. There is a Python notebook in Bobber and Mason's E textbook for HelioML. There is a chapter on what we call deep EM, and that is a machine learning approach, a deep learning approach for DEM inversions. Essentially, what we have is the inputs, the x's, are the AIA counts, the vector of AIA counts per pixel. The output is the differential emission measure inversion. And we can just use a bunch of inversions from the original IDL method as the training data and train a deep neural network to do the same thing, to mimic the same thing. Anyway, so you can go through this IPython notebook. And so actually, it works quite well, but surprisingly, it almost works better than the original method. So the right panel shows the emission measure map at log t of 6.3. There are actually fewer artifacts than the one in the middle. And it seems to be able to denoise the data. But also importantly, the deep neural network is about 4 to 5 orders of magnitude. No, 3 orders of magnitude. About 3 orders of magnitude faster than the original DEM method. So it means that when you have this, doing DEMs doesn't cost anything anymore. Okay. Okay, so another case study is to try to generate spectral irradiance measurements. Okay. Okay, so SDO has AIA, HMI, and Eve gives us the EUV spectra of the sun. But the Max-A channel stopped working in 2014. But why do people care about the EUV spectral irradiance? It's because that even though people care about X-rays impacting the upper atmosphere of the Earth, it's known that the EUV emissions are also very important for the energetics. But since 2014, the Max-A channel no longer worked, and we no longer had that spectral irradiance measurements. So this plot shows the spectrum, the yellow there in the middle there shows the Max-A channel. And then the hashes here are basically what the AIA channels, where the AIA channels are centered. So we try to regenerate this type of spectral irradiance measurements. But actually, the Eve team, they fit the strong lines from the spectrum. And so we take an easier problem. Instead of predicting the full spectrum, we predict the strongest lines in the spectrum, as well as the integrated irradiance over that channel. So from the NASA Frontier Development Lab team, what we did was we basically gave AIA images as inputs, and we trained a function to map those AIA images to the spectral line measurements that Eve measured. Okay, so For a lot of machine learning problems, you want to start easy first, so simple first. So the simplest thing to try is to just sum up the AIA images and possibly take the standard deviations of the images and fit a linear model to see if you can do a good job at explaining the Eve observations. And it does a pretty decent job, actually. So you start off with that. And then you can try to modify your model or improve on your model in order to do better. And so the way to do better is to first do the baseline model with the linear method and then use a convolutional neural network. What the convolutional neural network does, it essentially just picks out features in the solar images and uses those as it's like automatically generating features, but discovering the features in the data, and uses that to fit the data. So when we do this, we can reproduce the Eve level 2 spectral irradiance measurements to within 2%. I'm trying to get to the next slide. OK, here we go. Yeah, for most lines, the error is about 2%. And we also compared this with a physics model. The physics model is simply, we take the AIA data, we do the DEM inversion, we fold the, using Chianti to predict what the measurement would be. But it outperforms the physics-based model. The deep neural network outperforms the physics-based model. OK. OK, so this is an example of one of the lines. It's one of the harder ones. But OK, fine. You can say that, oh, it's not clear what physics you're learning from it. Well, we might not be learning anything. We know that there are imperfections in the DEM inversions because of certain assumptions about how you generate the temperature responses, et cetera. Nevertheless, I would argue that there are many things that we do as scientists in terms of how we handle our observation data and simulation data that we need to process it in a certain way before we can concentrate on learning the lessons and the physics. So I think machine learning is useful for that. And if you're interested in space weather, it's useful for that too. After training the model, you can rearrange it. You can rearrange the blocks so that from the images that you put in through AIA, you can synthesize actually spatial maps of the different spectral lines that we're reproducing before summing up to give the full disintegrated irradiance. So, and this is just a matter of a sanity check. It's not saying that we have reproduced a spatially resolved Eve. It's just to know that at least the spatial structures are consistent with what the sun is doing, and it's not just a fluke. OK, so with that, I would conclude with things that I have talked about. You can do a bunch of other things. I haven't concluded, sorry. I have a couple quick cases that I want to include. There's some interesting work from the Korean group on using 304 to generate magnetograms. It's slightly different than what Junwei presented because these are signed magnetograms. And in some circles, this is quite controversial because, well, how does it know the polarity? Because the thermodynamics should be invariant to the sign of B. So it should know the polarity, but it probably comes from the training data that you use a particular cycle. And when you look at it in detail, the AI-generated magnetogram compared to the real magnetogram is not all that great if you are interested in looking at the features inside active regions. Having said that, if you're only interested in the sort of flux in the active region, in terms of a global model, maybe it's not so bad. Maybe it's good enough. And so whether something is good enough depends on your science case. And I think we should be nuanced about it. So for example, Lisa Upton, who runs large-scale flux models, she thinks this is quite exciting and useful. But if you're like Durgesh and want to look at loops, coronal loops, I mean, and the relationship with magnetograms, it would be the wrong magnetic map for an active region. So this is another example of accelerating inversions using deep neural networks. So this is for the iris spectra for the magnesium 2H and K line profiles. They train a neural network, so that is about 1 million times faster than STIC. That's by Science Data et al. There are some other data processing things that we like to do that is hard. For example, tracking flows. People have local correlation trackers to look at the flows, but they generally have some limitations, and you can do a better job with a deep neural network. And this is open source, so you can try out DeepVeil from Asensio Ramos. And his group, they've applied deep neural networks, convolutional neural networks, to a bunch of other things, including Stokes inversion, and also to do inversions to get the quantities at constant geometrical height. That assumes that the model that they use to train is correct. But that's quite exciting if you can do that. So other things you can do is to use ML to help you with data assimilation, because there's a big chunk of machine learning that is about a posterior estimation. There's a lot of, actually all the machinery is about functional optimization. And then the deep learning frameworks are essentially things for doing computational graphs. So there's a lot of processing that you can code up in these frameworks that can be automatically scaled up and sped up by using GPUs or TPUs. And if you code them up so that they're automatically differentiable, you can also just automatically get an inversion code through propagating the gradients. So there's a lot more physics we can do with these machine learning frameworks. Yeah. So with that, thanks for your attention.
Questions?
That was a nice overview, Mark. So you didn't touch upon predictions of time series. And this is something that people are getting into now, and it's kind of a bit scary because people are looking at like past history of some phenomena, for example, the sunspot cycle, and using this to try and predict the future. So do you think dynamical systems which could, in principle, be chaotic, can also be predicted? And there's some work, along these lines at theoretical level. But the prospects are a bit scary. But do you think it's possible?
I think there are papers on solving PDEs that have some chaotic nature, and by using machine learning, they can actually do a pretty good job. And then there's also work on, like, for example, the Burgers or the Navier-Stokes equation, in order to go beyond the CFL condition or to have a subgrid model that works well. That also is helpful. So there's a lot of work in that. There's a lot more work to do, but one has to see.
Most of what I was saying looked like Greek or something, because we are of the old school. However, something strikes me that when you're looking for freaks, like as in freakonomics, when a machine predicts something, and then if you have actual data as well, and then it's different, then that's where you can concentrate your limited resources apart from machine learning. So maybe that helps that way too.
Yeah, in fact, there's anomaly detection, for example. One way to do anomaly detection For example, with financial transactions of like financial records, is they do so-called an autoencoder. It's one example to do it. So basically, you have your input data, and then you have some layers of the network, and there's a bottleneck. So you're basically doing compression. You're basically transforming it into a lower dimensional space, but then you bring it back up and try to reproduce itself. And by doing that, you're actually denoising the data, and it will do well for most of the cases that are reasonable. But the cases where it doesn't do well, that might be where the anomalies are, and that helps you detect that.
Any other questions?
Yeah, thanks, Mark. Just a point to make, because this AI-generated magnetogram, the way it is produced is quite encouraging for Aditya as well, because on Aditya we don't have magnetogram, and to compare the suit data with what the magnetic field is doing, we are banking quite a lot on what SDO HMI is going to give. So I hope there will be a lot of overlap, but if it doesn't, then we can use this kind of prediction and use the suit data along with. Or larger scale, of course, not very small.
Yeah, yeah. It'll be hard to be better than just using a gong magnetogram, though.
But the gong will be limited time,
right? Right. I mean, well, yeah.
There are 8 of them, but the number is
Great work, Mark. I have one question and comment. A question is like you're showing the DPM technique. Is it any inversion method specific, or is you can use any inversion technique?
Oh yeah, so you can just use any inversion technique to generate the training data. So the training data is then used to train the neural network to do the deep EM. So if you just follow the chapter, you can just use your whatever you can handle on contour or another DEM method. You can replace that data for the training.
Okay. And the comment is like, this is very useful, especially for predicting or planning for the sounding rocket missions, because just a couple of days before, we try to look for active regions or sunspots and then see which one to point at. So I think this would be very useful in terms of planning for our target observations.
So that's like if the active region is interesting or not.
Yeah. Yeah.
Oh, okay. So that goes to maybe flare prediction, and that's the next talk. So I will not comment on that.
Yeah. Sure.
Okay.
Any other questions? Yeah, yes, there, please.
My thing is that how good if the machine learning can we use to increase the resolution of a magnetogram? If we can do so, then how good the ML algorithm is?
Sorry, I couldn't hear the first part of the question.
Increasing the resolution of a magnetogram using the ML technique.
So last year, there was the team led by Andres Munoz and Paul Wright, where they work with a bunch of people who are experts in super resolution. And I think they have some results on improving the resolution of magnetograms. Yeah, and then there is also the work by Asensio Ramos et al. In doing that. In both cases, though, they haven't benchmarked with just doing a deconvolution of the point spread function and sampling to a higher grid as a baseline, which I would encourage people to do, because we know what the point spread functions of HMI is, for example.
Any other questions? No? Okay, so let's thank our speaker again. Our next speaker is Shamik Bhattacharya. Is that correct? Okay. And he's going to talk about supervised convolutional neural networks for classification of flaring and non-flaring active regions using line-of-sight magnetograms.
Thank you very much. Oh, no problem. Yeah. Yes. Wait.
Hello. Yeah. So good morning, everyone. So today I'll be talking about the supervised convolution neural networks for classification of flaring and non-flaring active regions using line-of-sight magnetograms. So as we know, a solar flare occurs when the magnetic energy that has built up in the solar atmosphere is suddenly released, and a strong flare can have severe space weather implications. Like it can be dangerous for astronauts, and also it can potentially damage satellites and also disrupt radio communication systems. So this machine learning methods have been used to develop flare forecasting models previously. Now the goal of this project, of our project, was to build a machine learning model, a deep learning model that can detect patterns in the magnetic field, in the magnetic fields that lead to flares. So this represents the schematics of our project goal. So we built a deep learning model that takes the magnetogram images, solar magnetogram images, and it tells us whether this magnetogram belongs to a flaring active region or non-flaring active region. Now this is a supervised machine learning approach. So we need labeled training data. So that labeled training data is obtained using the helioseismic and the helioseismic and magnetic imager on board the Solar Dynamics Observatory, and also we also use the solar flare events catalog provided by the geostationary operational environmental satellite. So and the output labels of the magnetograms is 1 if it belongs to a flaring class, flaring active region, and it is 0 if it belongs to a non-flaring active region. So the entire data we divided into 2 parts, as Mark was mentioning, that we need to divide it in train, validation, and test data set. So we took from March 2010 to September 2015 as the training and validation data, and October 15 to October 18 as the test data. So as you can see, the data set is not a balanced data set. That is, there are approximately 5 times more non-flaring active regions than there are flaring active regions. So yeah, and the deep learning model that we used in this case was a convolutional neural network. So convolutional neural network, these are very useful for extracting features from images, important features from images. So the convolutional neural networks, this uses filters of certain sizes to scan through the images, and this scanning process extract features from these images. Like in this picture, you can see this is a magnetogram image, and the light white circles, this you can consider them as pixels, and here the So we are using a 3x3 filter in this case. So what this filter does is that the filter scans. Okay. So this is the 3x3 filter. So this filter scans through the image and generates this feature map. So what does it do actually? The filter, when the filter is at this position, it will perform the convolution operation to generate one number. So what is this convolution operation? This is a very simple operation. So here, W0, W1, W0 to W8, this represents the filter weights. And A0 to A8, this represents the overlapping pixel values of the images. So this is doing this simple operations. This is known as the convolution operation, and then it is generating this one pixel. So, and then this filter scans through the entire image to generate this whole feature map. So after this convolution operation, we again do one pooling operation. So in pooling operation, we take a block of pixels and then extract some summary statistic from this block. Now this summary statistic can be average values of these pixels, or maximum value of these pixels, or minimum value. So depending on that, it is called max pooling, average pooling, mean pooling, like this. So now one important thing to consider is that the important features in the magnetograms, which classifies the flaring magnetograms and non-flaring magnetograms, they can be of different sizes because the active regions are of different length scales. So a larger filter or kernel is preferred for information that is distributed more globally, and will prefer a smaller filter for features that are small in size. So keeping that in mind, we chose the Google Inception CNN architecture. So in Google Inception CNN architecture, what is done is that instead of filters of one size, it uses filters of multiple sizes in one convolution layer. So here, this is taken from the original Google paper. So it is using 1 by 1, 3 by 3, 5 by 5 convolution, and another 3 by 3 max pooling operation in one convolution layer only. And after that, it concatenates these results to generate the output, to generate the input for the next layer. And so we created our custom Inception module based on the original Google module. So here we are using a slightly different size filters, 3 by 3, 5 by 5, and 7 by 7, and also 3 by 3 max pooling, and concatenating these results together. So this is the full custom Inception architecture that we built. So this is the magnetogram image, and this is the generated feature maps after the convolution operation. So here we are using 8 different filters. That is why it is generating 8 feature maps. After that, max pooling, and then again convolution, then again max pooling. After that, we are using 2 inception layers, 2 inception modules that I just showed. And finally, we are getting one output. Now, this output will be 0 or 1. 0 means the machine is predicting that it is a non-flaring. 0 means it belongs to a non-flaring AR, and 1 means it belongs to a flaring AR. Now, this output during the training process, what is done is that we supply this machine with this input images, and it generates one output. Now, this output will be compared with the actual output for this level data, and it will calculate a loss function. So during the training process, we'll choose the weights and biases of this network such that the loss is minimized. So then we'll say that our network has been trained properly. So, and another important point is that all of these magnetogram images are of different sizes. But this network will take input images of fixed sizes only. For that reason, all the magnetogram images were resized to 256 by 256 pixels. Now, so after the training part, we tested the performance of the machine using the test data. And our classification metric were this recall, where the true positive is the subpopulation of flaring magnetograms that has been accurately classified by the machine. And true negative is also same, and false positive is the non-flaring magnetograms that has been classified as flaring magnetograms by the machine, and similarly for false negatives. So we are using these 2 performance metrics. One is recall, and one is TSS, the true scale statistic. And here are the results. So for the positive class recall, we are getting 0.76. Negative class recall, we are getting 0.77. And the true scale statistic, we are getting 0.50. Now, in this model, we are not considering how far one magnetogram image is from the flaring event. So that is all of these magnetograms, if it flares at any point of time, we are considering it as a flaring magnetogram. So in that sense, we can say that the CNN performs reasonably well for this classification problem. Now, this plot shows how the recall changes, the average recall changes before and after the flares. So this plot is average over all of the flaring magnetograms. And so we can see that the predicted recall, and 0 represents the flaring time. So the predicted recall by the machine, it starts from a value of 0.6 and increases increases steadily and peaks at about 0.8 just after the flaring events. So here we can see that the recall does not change much a few days before and after the flares. And then we also saw that the machine output, the output predicted by the machine, it predicts between 0 and 1. It is also highly correlated with the magnetic flux of the magnetograms. So if the magnetic flux of a magnetogram is high, then the machine is very likely to say that this is a flaring magnetogram. And if it is low, the machine is very likely to say that it is a non-flaring magnetogram. And finally, we also wanted to see what the machine is actually looking into. This is done by the occlusion map. So occlusion sensitivity is a technique to understand which part of the image is most important for the model, for the deep learning model. So this can be done by blocking one part of the image and see the machine output. Then block another part of the image and see the machine output. By this way, we'll understand which part of the image is most important for the machine. And we saw that, we found out that for most of the images, this kind of region that is in between two opposite polarities, this is what the machine is looking into, giving more importance. In conclusion, we can say that the instantaneous recall remains high and constant days before and after the flares. And we also saw that though local features are important, but CNN is primarily looking into the total magnetic flux. We also saw that machine pays attention to the region between opposite polarities. And so we need to, we are also thinking of changing the CNN such that it focuses more on the local features in the images. And also we are planning to use additional data like the AIA data that we can add as another channel for the machine. That we are planning to do in the future. So thank you.
Thank you. Any questions?
Did you say you're using line-of-sight magnetograms for this study?
Yeah, line-of-sight magnetograms.
So you work in Shravan, right?
Yeah, Shravan. So
actually,
I did my PhD in atomic physics. After that, I changed my field. So this was my first project.
Okay, all right.
So, yeah.
So I think last year, the year before, Shravan published a work with some other students, perhaps looking at, again, machine learning applications for, in fact, Mark was also part of the team, solar flare prediction, right? So where they identified that the buildup of currents, which is kind of an extensive parameter, plays an important role as a predictor for this. So having done that, why would one take a step backward and then go back to line-of-sight magnetograms? Because you are losing information, right? I mean, if you're using a system where you don't have the information of currents because you're using a line-of-sight magnetogram and only flux, you are forcing the machine to work with what you have, which is a limitation, right? Okay. And that flux is an important predictor, has been known forever, right? So why would you not use more relevant, full vector magnetic fields to do this kind of work? Because then you are, in principle, having the full parameter space available for the machine to learn from.
So, that particular project I do not know about, what you're talking about, what Shravan was doing.
So I'd like to comment on that. So yeah, it is obvious that vector magnetic field data is it is going to give better results. But we don't know how the machine is going to process the magnetograms, right? Because these are not the kind of images for which the CNNs were designed in first place. They were designed to look at images from day-to-day life, like faces, cars, and stuff like that, but not magnetograms. So this, through the primary goal of this project was to understand how a machine processes these kinds of images. So if you take a magnetic field map, so what you see is you have magnetic regions of different scales. These are the features basically. So the idea was to start with line-of-sight magnetograms and then move on to vector magnetograms, like as 3 different channels. But so we were just trying to focus on the interpretation part.
I think we'll give the opportunity to a student to ask questions first.
So I have a question on TSS. If you could please go back to the slide. Okay. So in TSS, there are 2 terms. On the right side, there is this true negative. So to me, it seems like because the data is so imbalanced, true negatives could be very large and on the right hand side, so it will make the right hand side terms smaller.
Right hand side is the pure false positive.
I mean false positive divided by true negative plus false positive. So because there will be a lot of non-flaring cases, so the true negatives could be, could have a advantage. Like it can be very large. To me it seems like that. So would you please comment on that?
What are you saying? If true negative is less, you're saying?
True negative should be large because
Achha,
data is imbalanced. So there are so many non-flaring cases.
See, it is subtracting the recall from the recall. It is subtracting the false positive rate. Okay, so yeah, means in recall you can see that only we are considering the true positive rate. Okay. The false positive rate we are not considering. So yeah, but in the TSS we are subtracting this.
In the TSS.
Yeah, in the TSS we are subtracting this false positive rate from the recall.
Okay, so maybe I will discuss it with you later because to me, as you explained on the right hand side, true negative is the population of non-flaring magnetograms, and that's supposed to be very large for this data set. Maybe we can discuss it later. Yeah, thank you.
Okay, I think we will need to move on. Thank you for the interesting talk.
Thank you.
So the next speaker is Divya Oberoi, and the title is Solar Radio Imaging, the Dawn of a New Era.
Okay, so good morning, everyone. Yeah. Sorry. Okay. Yeah, my name is Divya Oberoi. I'm from an institution right next door, less than 100 meters from where you're sitting. I'm happy to have this opportunity to talk to you about some work which we've been doing in the radio part of the band. And I want to start by listing my various collaborators on this. So the names in italics are students who have worked with me on this. The names in bold are students who are continuing to work with me. And we've also recently started to work with a commercial enterprise by the name of ThoughtWorks. Okay. So the rough plan is basically that I'll introduce to you first the instrument I've been working with, and then our unsupervised interferometric solar radio imaging pipeline, which is the sort of key centerpiece of this talk. Show you some results of the images which have come out of it, the science they have led to, and our explorations of, our very initial explorations of the field of AI and ML. And want to end with telling you about the availability of the MWA data and the air cars. But to go back to the title, the new era which I'm talking about here is basically, at least my sense, that we are entering a regime where the use of large-scale automated pipelines and things like machine learning will become essential to extracting science from the data which our instruments are now giving us. Okay? So here is a view of one of the tiles of the MWA, which is located in Western Australia, sort of inhospitable part, population density of about 0.3 millihumans per square kilometer. But what you need to know about this instrument is that it works in the frequency range from 80 to 300 megahertz. It has 128 of these spread over somewhere between 2 and 5 kilometers. We have a little bit like the VLA different configurations. So you can use these tiles spread over as little as 2 or as large as 5 kilometers. This gives you an imaging resolution of half a second and 40 kilohertz. In frequency, at any given time, we can cover about a 30 megahertz bandwidth. Okay? Here is an example of the data from the array. The x-axis is frequency broken into some 12 chunks of 2.5 megahertz. Y-axis is time, about 5 minutes of data. Time resolution, like I said, is half a second. What I want you to notice here, basically, are these many thin slivers of emission, which you see here. This is a time when nothing was supposed to be happening on the sun, right? None of your standard instruments have detected any flares, anything significant which is happening here. But there is all this evidence of presence of non-thermal emission, which is coming from the corona. The fact that this is changing so rapidly in time and frequency requires you to image these data with very high time and frequency resolution. Otherwise, you're going to sort of smear things over. And the beauty of the MWA, it's not supposed to turn that way there. The beauty of the MWA is that for every pixel on this plot, I can make an image. And if I was to really do this, I will end up with almost 500,000 images every 5 minutes. Now that is clearly a task which is not up to a human. For that, you really need some sort of an automated pipeline to be able to deliver that. And that is what we've been trying to build. The other thing which I want you to realize is just a little bit about the nature of radio interferometry, that it's a Fourier imaging technique. What each of the baselines of the interferometer is doing is measuring one Fourier component. You gather all of them from your array, and then you invert that to make an image of the sky. Now, because your sky, or sun in our case, is changing so rapidly, you must gather all the information you need over a very short time and frequency span. This image on the right-hand side shows you the locations in the Fourier plane where the MWA is measuring these data. Okay, and it is the inversion of the information which you would have measured is going to lead to your image. Because you want to capture a lot of information, naturally you would have a very high data rate. So in our case, our data rate is about getting close to a terabyte an hour. And we are planning an upgrade which will give us 16 times as much data. So, but right now we are at about a terabyte an hour. In the MWA archive, currently there sits 3.03 petabytes of solar data. Okay. Now, the process of making a radio image by its very nature is iterative. It has a part which has to do with calibration of the data. You use your calibration to get an image of the data. You use your image to improve your calibration. Use the improved calibration to get a better image and keep iterating till you're happy. In addition, the process of imaging itself is iterative. For those of you who know, it's a clean-based process, which is you're going to pick up a lot of independent flux components in each of the clean iteration. So traditionally, this has been very interaction intensive, very effort intensive, along with being compute intensive. Okay? And here is an example of the number of iterations in this cycle, calibration, imaging, and back to calibration and imaging again. Order 100 is very typical. We often do more than that if you want to extract good images or low-level features in your images. Okay, so this, I think, is the most remarkable success we've had in the recent past. This is what I'm trying to show here are the results from our unsupervised, automated interferometric imaging pipeline, which we call air cars. These two images show sort of two vastly different states of the sun. On the left, you have more or less the quiet, featureless sun with brightness temperatures of order 10 to the power 5. And on the left there, you have a bright type 2 source sitting at the edge of the sun with brightness temperatures going out to the range of 10 to the power 9 Kelvin. So they are 4 orders of magnitude apart in terms of the brightness of things which you are seeing there, but both of them have passed through the same pipeline without any human intervention. This is a case which is, as far as radio imaging is concerned, it is easier to deal with. We are able to extract a dynamic range as high as 10 to the power 5. This is a case which is hard. When you have sort of featureless, large, extended sources, it is hard for interferometric imaging to get good dynamic ranges, but even there we managed to get something like 1,000. So the key points I would like you to take away are that we now have a robust, unsupervised pipeline. It has led to an improvement in the imaging dynamic range by 2 to 3 orders of magnitude over what has been the norm in traditional radio astronomy. So we are now the state of the art, and naturally, if you're going to be exploring a sort of phase space which has never been available, it is going to lead to some interesting science, and I want to give you a few examples of that a little bit later. To tell you a bit more about aircars, it's based on CASA, which is the current, I guess, most commonly used interferometric imaging software, developed primarily by NRAO in the USA. But the design of aircars allows you to use flexibility of other software. No external dependencies. It's designed so that a non-expert can actually make a reasonable choice, already has a good starting point to work with. For the expert, you can tune it the way you want. You can tune the performance to various things which you want to do. So this is basically our attempt to make interferometric imaging of MWA data accessible to the non-expert, but to a well-informed user, right? If you'd like to try it, please get in touch. I just realized I'm running really behind, so I'll skip over a few slides. This is pre-air cars, but this is here just to give you an example of the small things which you were seeing earlier, how different do they look in the image plane. This is the same time slice, but different frequencies, roughly around 5 megahertz apart. This is the same spectral slice, different images about 1 second apart, just to give you a sense for how things are changing across time and frequency. Something we came up with is something we call the spatially resolved dynamic spectrum. You're all used to dynamic spectrum. It just integrates the flux from the whole of the sun. What these guys, A1, A2, A3, et cetera, are showing you are the flux which is coming from something which is about the size of one resolution element sitting at that place. And it tells you that different things are happening at different places, quite naturally, not a surprise. There's just a tool to help you visualization. Here's another sort of visualization. There are 48 frames here, each corresponding to different spectral channel. Each frame is half a second. A total of 23,000 images have gone into that. And it just tells you the whole nature of the range at which things are changing in this. This is an example of the same data, just shown differently. This is just stacked one upon top of each other, high frequencies at the bottom, lower frequencies on top. These two frames are just a few seconds apart, right? To give you an example of the sorts of things we've managed to do, lack of time, I'll just want you to focus on this one. The blue here is the integrated flux density from some small spatial scale source. The red is the size of that, the area of that. What is obvious if you stare on it is the anti-correlation between the integrated flux density and the area. For every peak in blue, there's a valley in the red. This was something which was never known before, and it took around 20,000 images to get to the fact that something like this is happening. This was an image which you saw yesterday in Surajit's presentation. This was a faint extended emission which is arising because of gyrosynchrotron emission from the CME. Debajyoti has a poster on this outside if you want to take a look. This has now allowed us to detect gyrosynchrotron emission, or at least what we interpret to be gyrosynchrotron, out to as far away as 7 solar radii from the center of the sun. Okay, this is another thing which was enabled by this air cars because it took something like 33,000 images to get to the statistics which we wanted to get. What these histograms are showing you are the first detections of faint non-thermal emissions from the quiet sun. We go down to roughly millisolar flux unit levels, which are about 2 orders of magnitude weaker than what has previously been reported, which was also incidentally our own work, which was an order of magnitude deeper than the rest. Okay? And this gives really tantalizing but indirect evidence for nanoflare-based coronal heating. So currently, we are working on things where we know how to extract information from the images. Tend to work with things which are well-defined in the image plane, or at least where we can define a statistical description which we want to get after. But if you just look at it, I mean, there are tens of thousands of images. It's humanly impossible to assimilate that information just by browsing through those images. So we have no choice but to look for some better tools for doing this. That's what we are headed towards. So this is not quite a supervised learning, and thanks to Mark for an excellent introduction to this whole subject. So this is not really a supervised learning or a classification problem. The way we are looking at it, at least, is to think in terms of feature extraction. And we don't even want to define what the features are, because we believe that there'll be relationships between different features, which we don't necessarily want to bias by telling it to look only for things which we think should be there. Right? So we think this is a really fertile ground for data-driven discovery, but we are just venturing into this right now. About the MWA data, it has a proprietary period of 18 months, but beyond that, it's all public. We have been observing since 2013, so there's plenty of public data. And given the size of the groups of people and how compute intensive it is, only about 2 to 3% of the data has been looked at. So there's plenty out there. We are continuing to work on aircars to develop it further, but the aircars version 1 is available on request. It's basically me and 2 grad students, so we don't have a whole lot of support to offer. But if you would like to work with this, you're welcome to get in touch with us. We would like to really help you. There's at least one location outside the MWA project where it is already in use. The big thing in the next version would be polarimetric imaging, but we have still some way to go for that. Okay, so I'd like to just summarize by saying that I think we are entering an era where automated imaging and information extraction tools are increasingly becoming essential. I mean, there is no other way to go forward. And aircars, I think, is a significant achievement for us. It's a robust tool for imaging MWA solar data. All the same principles, incidentally, will apply to the SKA1 low as well. So this tool should just carry forth just the way it is to SKA low. We are happy to make it available to the informed community. If you are interested, please get in touch with us. We're happy to support. MWA data is public. We invite you to come and make use of it. We begin to explore artificial intelligence and machine learning methods. We're happy to learn from those in the audience who have suggestions, ideas about interesting things for us to pursue. So I think we really have exciting science prospects in the future and look forward to that. And I'll stop with that, yeah.
Any questions? Maybe let's the student first.
I wanted to know which clean algorithm is used in that pipeline. And another thing is like, how long does it take for the complete process to make an image out of it?
Okay, so the pipeline is using, currently using only the algorithms which are already available within CASA. So it has not implemented any additional algorithm. The key is figuring out how to be able to drive these algorithms so that all the subjective decisions which an astronomer typically makes, if this process has converged or not, or should I clean deeper or not, that is, all that heuristics is automatically taken care of. Sorry, what was the second part? How long does it take? Yeah. Okay, so fortunately, this problem does not require much RAM. Okay, it requires just a few tens of MB of RAM. So if you give it a few gigahertz, say 2.3 gigahertz is the CPU which we use, it's about 10 to 15 minutes for calibration plus imaging per image. If you want to do just imaging, it is between 1 and 3 minutes depending on the complexity of the source, typical numbers. Yeah.
So you said that the MWA data is public.
Yes, please. Yeah.
So that how many events you observed and how can we can get our data? It is open to the website?
Yes. So yeah, I should have mentioned that. Sorry, extremely useful question. So we've been observing typically about 100 hours per semester. So about 200 hours per year is what we have been observing, though there was a while in 2014-15 when we were observing for much longer than that. So that is the data which is available. The interface, so if you just search for MWA, virtual observatory, it will get you to the web page which has the interface. You will need to ask for a login account, which the administrators will give you. It allows you to search by date, what data is available when. Yeah. So that interface is available to you. So it will hide the proprietary data and show you everything which is in the public domain.
Thank you.
Yeah.
Any other questions?
Deepa, so what I wanted to know is how are you training your pipeline? Because
so this pipeline has been trained by humans. So we looked at sort of the variety of various cases which we encountered during our course of working with the MWA data. So basically the decisions which you need to make are a little bit about heuristics, about when is it enough, or can I extract more from these data, so I should continue to refine my calibration. So the answers are sort of twofold. It depends a bit on your science objective. If you're looking at some really bright sources, you don't need to go down to a fraction of a percent in terms of the flux which you are looking at to extract the information which you care about. In some other cases, when you're looking for really faint features, then you need to push your imaging dynamic range a bit more. Those parameters the user has control over, but where to terminate based on the requirements which you have imposed, there is some heuristics which is built into it. That's not really a part of artificial intelligence, that's really human intelligence here.
Any more questions? Okay, so if not, let's thank all three speakers again. So, any announcement before the tea break? No. Yeah, we convene at. Okay, we meet at 11 o'clock.
Hello. Hello. Hi. Yes, yes, I can hear you. Okay. Okay, thank you very much. Open my camera, okay? Let me try. I don't know how to. Oh. It works. Yes, I can see you. Okay. Okay, thank you. Okay.
Welcome everybody. So this session is going to start now. So first talk is by Jin Huang. Jin is already online, and we'll start Jin. Yeah. Jin, can you hear me? You can start now.
Yes, I can hear you.
Yeah. Yeah. You can start.
Okay.
Yeah.
Okay, thank you. Good morning, everyone. Thank you very much for giving me this chance to share with you on the topic of solar flare forecasting models, past, present, and future from the perspective of machine learning. I'm Xin Huang from the Solar Activity Prediction Center, NAOC, National Astronomical Observatory, Chinese Academy of Sciences. Today I want to share 3 points. Why we need a solar flare forecasting model? Can we build a perfect flare forecasting model? And what can we forecast? Solar flares accompanied by the high energetic particles and the radiation could disturb the radio communications and the astronomy. Its related CMEs may cause a geometric storm, so we need to build a solar flare forecasting model, and the influence of the solar flare can reach the Earth within 8 minutes. The next very important question is, can we build a perfect forecasting model? The perfect forecasting model means using this model, we can forecast the precisely the level, set time, and the location. Let me look at this figure. The flare frequency and its peak flux obeying the power law distributions. So it indicates us the solar flare can be explained by the self-organized criticality model. In this model, the events occur randomly. So I think the answer is no. We cannot build a perfect forecasting model. And from now on, all the forecasting model is the probability model. What can we forecast? There are lots of work for the yes/no forecast. Yes/no forecast means whether or not a flare will happen within a given period. And there are few works to focus on the onset time, and I cannot find a paper to focus the flare location forecast. Let me look at the no forecast. The first paper to the solar flare forecast is in the 1930s. And the first machine learning method used in the used to build the solar flare forecast model in the 1980s. And then with the development of the artificial intelligence, there are lots of machine learning algorithms applied to build the forecasting model. This is the solar flare forecasting model. It is a probabilistic model. In this model, a probabilistic relationship between the sunspots and the solar flares are determined. In 1980s, the Space Weather Prediction Center in Space Weather SWPC, they built expert system for the solar flare forecasting. And in this model, the solar physicist designed more than 700 rules. These rules can be used to give the solar flare forecasting results. And after 2 years later, a NIPS paper shows us using a neural network, we can learn the relationship between the sunspots and the solar flares. After all, lots of work are used to build the solar flare forecasting model. In this traditional machine learning method, the very important thing is to extract the features from the active region, and then the machine learning method is used to build the relationship between these features and the solar flares. The traditional machine learning method, the features is the most important thing. We can see the very famous Macintosh classification of the sunspots, and these features are used to characterize the property of the active regions. We can use the line of the magnetic RAM in the active region, and also calculate the velocity field parameters and the energy parameters. This paper compare lots of magnetic field parameters of the active regions in the solar flare forecasting model, and they found all these parameters has limited forecasting capabilities. So very important question is, can we automatically extract the features by using a neural network? In this review paper, shows us our this is our paper published in 2018. This paper is the first attempt. In this paper, we directly input the magnetogram of active region into the neural network. This neural network is in this neural network, there are two parts. The convolutional layer and the full connected layer. We use this convolutional layer to extract the features from the magnetogram of active regions, and we use this full connected layer to learn the relationship between these features and the solar flares. That's our learning results. These are the weights in the convolutional layer. We can say we initiate the weights with a random number, and after the learning process, we can get some forecasting patterns, and these patterns are learned from the a very big data set. So what the neural network focus on? That's an example. In this example, this highlight area is the important area. The CNN find. We can the model think near the neutral line. This magnetogram is very important for the flare forecasting. And the TP rate, TN rate, FP rate, FN rate, and some skill score will evaluate the performance of our forecasting model. Our testing results for the 6 hours, 12 hours, 24 hours, and 48 hours for different flare level for C and X flares. We can say we can learn the forecasting patterns directly from the magnetogram of active regions. And the paper shows directly input the full disk images of the sun. And using this more complex neural network, they directly input this full disk image and give the flare or no flare forecasting results. Next, I will talk about the onset time estimation. There are not much work to do this, and Marina's paper, this paper, is the first paper to do this work, to do the onset time estimation. In this paper, they find the relationship between this U shape and the onset time of the solar flare. And this U shape is the magnetic field parameter sequence. In another paper, they build the onset time estimation model using the regression method, the SVM regression method. And recently, we find that we can build a rolling forecasting model to estimate the solar flare onset time. In this forecasting model, the forecasting model outputs the forecast results for every 86 minutes. That's our that's our example. The cadence is 98. Sorry, 96 minutes, and every 96 minutes we give forecasting results, and this red one is flaring, the probability of flaring forecast, and this blue one is the probability of non-flaring forecast. We can find we can get a cross point. This cross point is our estimated onset time for the solar flare. And below is the true status. And we use this method. The forecasting error for the onset time is within the 24 hours for the more than 80% samples. In fact, as we know, the solar flare, flares originate from the release of the magnetic field. But we can only observe the magnetic field of the active regions in the photosphere. However, the solar flare happens above the photosphere. We can calculate the 3D magnetic field of the regions, and using this 3D sequence data to do the to build the solar flare forecasting model in the future. And in the real world, there are lots of 3D data. For example, the CT data, and some CAD model data, and geology data. And the machine learning community developed the 3D deep learning method for the 3D data. For example, this multi-view convolutional neural network, 3D convolutional for the 3D data, for the 3D shift net, and the VoxNet. Now we have some preliminary results for using the 3D data. Using the potential model, we can get the 3D data for the active regions, and we input this data into a neural network at the different height. This is for the different height, and this for the vertical exercise for the performance. The red one is the true skill score, and let us look at the red one. This means we can get the best performance for the solar flare at this height. And from these results, show us even use the potential model, we can improve the performance of our solar flare forecasting model. Our conclusions for the forecast at the beginning, we use expert systems. In expert systems, solar physicists extract the features, and solar physicists design the forecasting rules. And in traditional learning method, solar physicists extract the features, and machine learning method learns the forecasting rules. And in the deep learning method, machine learning algorithm extract the features of the active regions, and machine learning the machine learning algorithm learns the forecasting rules. For the data, we use the 2D data, the magnetogram or some images of active regions, and then we can use the 3D data based on the explanation method, and then we can use the 3D sequential data to improve the performance of the solar flare forecasting model. That's all. Thank you.
Thanks, Jean. Questions? Okay, I have a question for you. Is when you showed your work on 2018 paper, so the network you showed, is that the single layer network at the very beginning? Yeah, no, like, yeah, this one. Is this the single layered network?
This one.
Yes.
That's our that's the structure of our forecasting model. We use only two convolutional layer to extract the features, and three fully connected layer to learn the relationship between the features and the solar flares. Okay. We do not use the more complex neural networks because we don't have enough flaring data to train a bigger or complex, more complex model.
How successfully can you do this with this kind of 2 layers network? How successfully you can predict the flares?
Yes.
Percentage wise?
For the 24 hours for the M flare, we can get more than 80% for the TP rate and 80% for the TN rate. That's our results.
Any more questions? Otherwise, thanks Jane again. We'll move on. The next speaker is Kyuhon Cho.
What is the? Okay. Thank you. Namaste, everybody. My name is Kyuhyun Jo from Seoul National University. So I would like to talk about the solar rotational tomography. I think all of us are interested in the state-of-the-art techniques such as deep learning like that, but my work is based on the very classical way. So tomography is the way of the three-dimensional reconstruction of weight of a three-dimensional volume using many different angle observations. So the object should be optically thin, and we need many observations at different angles. So usually, as I know, there are two types of the tomography. First one is filtered back projection algorithm, and second one is iterative reconstruction. So for the FEP algorithm is based on the analytic solution, so it is very fast and it needs a very low computational cost, and it's 10 or more than 100 times faster than the iterative reconstruction. So usually the diagnostic radiology use this FEP algorithm because the patient cannot wait for the calculation time. On the other hand, this iterative reconstruction use the very heavy matrix calculations. So maybe deep learning may use this iterative reconstruction. So this iterative reconstruction can reduce the artifact and noise, and so it can make better quality three-dimensional volume, and if it can only limited observation, it can use the reconstructions, and they can deal with the several constraints. So usually in science there are many observational constraints. So people use this iterative reconstruction. So my purpose is that using this FEP algorithm, we can infer the three-dimensional information of the solar corona. This is my goal. So let's think about the solar rotational tomography. So solar corona is, as you know, optically thin object, and sun is rotating. So we can obtain the many different angle observation at one position near the Earth. So it is advantage, but there are some disadvantages. For example, so solar corona evolves. If you take the CT scan, you must not move during that period, but sun is changing. And the most serious problem is this one, the blocked backside area problem. Let's think about this blue plane. We cannot see the backside. So it means that this coronal environment is not fully optically thin, because we cannot see this, we can obtain this information at the backside of the solar corona. So people mainly use this iterative reconstruction because it is one of the important constraints. So, but some exceptional case is using the FEP algorithm. There are some exceptional case studies, such as polar plume, because in the polar plume, like thing is free from these constraints. and some people use the coronal radial structure to use this FEP algorithm. So I will use this FEP algorithm for the solar rotation tomography. So let's think about this three-dimensional reconstruction. We can think that this three-dimensional reconstruction is the series of two-dimensional reconstruction of the latitudinal plane, like this image. And the stack along the solar rotation axis in this plane, the reconstructed 2D plane, we can have this three-dimensional volume. So there are two assumptions. The equality plane is perpendicular to the solar rotation axis and the parallel beam projection. So the problem is to move on the how can we successfully reconstruct the two-dimensional latitudinal plane using the filtered back projection algorithm. So we must resolve this blocking problem. So I made this test image. So this cat, do you remember this cat? In every lunch time, we can meet this cat. I will meet this cat in 1 hour later. so this, let's think about this the test image and think about the observer is located in the bottom side. Then we can obtain this one-dimensional array integration along the y direction. So formulation is like this: the integration y direction. Then let's perform the Fourier transform over this x direction. So we need one more integration and exponential term. Then let's think about the two-dimensional Fourier transform of this test image. So 2 integration and 2 exponential term we need. Then let's compare these two formula. If ky equals 0, then these two formula is exactly the same. It means that what is the meaning of the ky equals 0? It means that this red line. So basically, if we obtain one observation, we can fill one line in the two-dimensional Fourier domain. So if we have many direction observation, we can make this kind of sinogram, which is the bundle of the observational data as a function of x and the rotation angle theta. Then after the one-dimensional Fourier transform, we can fill the two-dimensional Fourier domain in everywhere. Then after the inverse Fourier transform, we can obtain this original image. It's the principle of the Fourier FEP algorithm. So this movie shows the process of the FEP algorithm. So combining many direction of the observation, we can make this from this original image to this reconstructed image. So we need a very tight angle interval observation. So this is the original image and the reconstructed image, and this is the difference between two images. So green color represents there are no difference between two images. So this histogram is the difference histogram, and this is the standard deviation. You can find that this FEP algorithm is well working. But as you know, the solar rotation tomography is slightly different. We cannot obtain the information inside the solar corona, inside the solar interior, and we cannot obtain the backside. The inside is okay because we cannot obtain this information in every angle, so we can consider it is some kind of cavity. But region 4 is make some problem because if observer is in here, we cannot obtain this information. But if we are in here, this region contributes the information. So sometimes shown, unshown, so it makes some error. So this is the result, and the same way. You can find in the difference image there are many systematic errors, and also histogram and the standard deviation shows it's not working on the solar rotational tomography. So this is comparison between the traditional and the solar rotational tomography. So I organized about more than 1 year to solve this problem. So I found some solution, simple solution. So this is the whole data set, and this is the observable area when you are in here, then we need the backside information. How can you get this information? The opposite direction observation. So combine these two information, we can make this whole data set. We call it this is modified sinogram. So it's very simple. So this is the result. It looks very nice. The all difference images shows the green color, and the center of the histogram is near the zero, and the standard deviation is smaller than the previous one. So this is the comparison between the typical way and my new method. So I think it's comparable. So I test my work to the real solar observational data. So I collect 2019 February whole data set in every step, 30 minutes and 60 EV channels and 32 by 32 binning, and I adjust the differential rotation for each latitude and plane. So the compute time is about 2 minutes to make this 128 box cube. So I tested these three different ways: the synthetic 193 angstrom image, and 3D-dimensional distribution of the electron density and temperature, and the synthetic coronagraphic PV image. I made this one. I will show you. So using the FPP algorithm, we can obtain the 3D-dimensional distribution of the 119 angstrom intensity. And after the line of sight integration, we can make this synthetic image of the 119 angstrom. So left one is the real observation, and right one is my synthetic image. So you can find that the bright region is located in the same region, and also the corona hole, you can find that. And this is the comparison between the observed image and synthetic image. And this is difference image, and this is the histogram of this difference image. The histogram shows that the center of the most of the pixel has near the zero value, and there are some deviation at this circle region, which is the bright region. So because in the bright region there are many coronal loops, and they evolve as the time goes, so it generates some error. But it looks good, I think. Then, second, I obtained the three-dimensional distribution of the electron density and the temperature. So using the DM inversion method, we can obtain the emission measure for each temperature beam. So by definition of the emission measure, we can obtain the electron density scale distribution of the using the tomography. So we can obtain the electron density and the temperature using this formula. So this is the result. This is the Carrington map of 193 and 171 angstrom, and this is the electron number density map as a function of height, and this is the electron temperature map as a function of height. You can find that the higher height shows the lower electron density, and you can find the latitudinal dependence, and the bright region has the higher temperature, higher electron density. So it is the electron temperature map. So you can find that the regional dependence, and the bright region has a higher temperature. And this more detailed analysis, I select two sample regions, D and Li. D represents the corona quiet zone, and E represents the south pole corona hole. So this is the electron density plot as a function of height, and the different color represents the different the spherical symmetric model. So this D, the quiet zone region shows the result of the quiet zone is close to this Cram model, which is the solar minimum quiet zone model, and this region E, corona hole model, is close to the Kutakula model. So it is this is the observational based corona hole
electron density profile. So I think my result is comparable to the consistent with the previous result, and this is the temperature comparison in quiescent and the corona hole. So you can, I think all of this, my result is comparable to the previous result. So the third one is the synthetic coronagraph polarized brightness image. So now we have a three-dimensional electron density distribution. Then we can calculate the Thomson scattering. Then we can obtain the coronagraph PV image. This is the real observation. This is the synthetic coronagraph image. So for more detailed analysis, I draw this brightness profile as a function of a position angle, like this one. And you can, the dashed line is the real observation, and solid line is the reconstructed data. So you can find the similar trend. The pole region has the lower brightness, and near the equator region, higher brightness. And you can find the height dependence also is very similar. So this is my end page, last page of this presentation. So I developed the FEP algorithm for the solar rotational tomography. So we can generate the modified sinogram and reproduce the synthetic image, physical parameters. And this, the most advantage of this FEP algorithm is that it's very easy to understand, and low computational, it needs only low computational cost. So something I want to note that only we cannot deal with this temporal evolution of the solar coronal structure. So we must use this this method to more than 2 weeks lifetime structures, such as the coronal hole or polar plume or something like active region like that. And so one of the questions is that this method heavily rely on the DM inversion method to invert the physical parameter in the solar corona. So we must carefully choose the fitting parameter or the DM inversion method. I think the Mark Chung already gave me some insight, because the DM inversion result is using the deep learning is better than the classical way. So, okay, that's all. धन्यवाद.
Let's keep on. So, questions? I have some. So when you do, so how many different angles do you need to have the proper 3D reconstruction?
It depends on the box size, but usually the 30-minute time cadence is okay.
Okay.
So the total number is about 1,700.
Okay. And so when you are calculating density from this, so what is happening is evolving in time. Suppose you are calculating the density of the active region. So this is evolving in time.
No, this method only shows the about 1 month average result only. No time evolution.
Okay.
Yeah.
Thank you.
Thank you. Extremely interesting talk.
Thank you.
And do you think something about systematic applying of your methods to HMI data, to MDI data, and where is available in future maybe?
Yes, I think the AI is okay because AI, the corona is optically thin, but MDI or HMI is not available in using this method because it is not the optical. It's totally different from the optically thin region. So yeah, but the maybe UVI on the stereo maybe can apply. Thank you.
Any more question? Let's thank the speaker once. Next talk is by Andreas on European Solar Telescope.
Sorry for this adapter issue. It was there when I tested it. So I want to give you an overview about the European Solar Telescope. It was supposed to be given by Luis Bellarubio. He could not make it to this conference, so I'm talking on his behalf. I want to start with a simple comparison to find out how important high-resolution observations really are. You see here on the left satellite image of Europe and on the right of India. And if you look at this low resolution, you can identify similarities very easily. You find at the same, you find mountainous regions, also they are maybe a bit higher when you go to the Himalaya. You find the sea in blue, you find more fertile areas in green, and dry and desert areas in the brownish color. So many similarities if you look at this resolution. The details reveal when you look at high resolution. So for example, if you look at a region in Germany, around Berlin, this is what a typical crossing looks like during rush hour in Germany. A lot of traffic, a lot of cars piling up at the traffic lights. But if you go then and look at the same high resolution observation in India, then it looks like this. You see that it's very important that we do observations in high resolution because the same feature might look completely different when you look at it at high resolution. What high resolution can do was very nicely demonstrated already with the first light of the DKIS telescope. A first glimpse of what high resolution solar observations in the future will look like can be seen in these titanium images at 789 nanometers, which were published last week. And they really reveal the details of the solar convection in these images. I'm really curious to see what happens when we not only see the broadband images of DKIST, but also narrowband images, and later then even polarimetric measurements. The amazing feature you can see here that even from the ground, you can achieve the high resolution, you can have very high stability, you see almost no flickering of the image, and you also can achieve a very high contrast, which is one of the strengths of the DKIST telescopes. So you can ask, why should we build another 4-meter telescope? Why should we even think of building an EST? And yeah, that is of course a valid question, and one has to find topics which are complementary to what DKIST can do. So when we thought about the EST design, we then thought about several options. So DKIST, for example, is an off-axis telescope. Off-axis telescopes have no central obscuration, and this absence of the central obscuration gives you a better, a lower stray light, a better PSF, very good for coronal observations. We decided to go for an on-axis Gregory configuration, and this on-axis configuration has the big advantage that you have every optical element is in a symmetrical light path, which gives you much better polarimetric accuracies. In addition, this on-axis configuration allows the telescope to be built much lighter. Also, another difference to DKIST is that instead of having the closed dome with air knives, our strategy is to build on an open dome. And this open dome will lead to a laminar wind flow over the telescope. And additionally, it also allows for a lightweight construction of the whole dome. And both facts, the on-axis design and this open concept, makes the whole structure much lighter. And the big advantage is that we can build a higher tower, and this higher tower will minimize the main cause for disturbing our observations, which is the ground layer seeing. The higher you are, the less ground layer seeing you have. Yeah, we also concentrate, of course, on the high precision polarimetric observations because of the on-axis design. We want to have complementary instrumentation to the DKIST telescope, and of course, by combining DKIST and EST, we can also increase the temporal coverage and observe one region over a longer period of time. So I want to first concentrate on these high precision polarimetric capabilities, and that is something which is illustrated here. So in the original concept, when we started to think of EST, we had 14 mirrors, and these 14 mirrors we could now reduce to only 6 mirrors, 5 of them active and 1 transfer lens. That increased the photon efficiency of EST by a factor of 2, and these 6 mirrors we have, they are all here at the top. M1 is the big 4-meter mirror, then we have an M2 mirror, and then this the 4 mirrors following are all active mirrors, and these active mirrors have are making up the MCAO, and all these active mirrors are also polarimetrically compensated, so that in the end, after all these 6 mirrors, we have really no instrumental polarization introduced. So the telescope Miller matrix is unity for all wavelengths, elevations, and azimuths of the telescope, and we can achieve a polarimetric accuracy down to, or even better, of 3 times 10 to the minus 5. A highlight of the telescope is the M2 mirror. The M2 mirror will be an active mirror, and this M2 is an 80 centimeter mirror, and it will be the main mirror for the adaptive optic system. It will have 2,200 actuators, and this is a technical challenge because other than for nighttime telescopes, these piezo's behind the mirror, they have to have a much larger pitch because the daytime seeing is much more violent, more turbulent than the nighttime seeing. And in addition, they have to be much faster, and they have to compensate with a much higher thermal load. So there are technical challenges for that, but the solution for that, we are optimistic that this solution, that this will be solved. An important thing which I want to mention is that this optical design with this 5 active mirrors from M2 to M6, all the mirrors are active, has a significant advantage in correcting the image. So we have several types of seeing degradation. We have the so-called ground layer turbulence. This is more or less the same during the whole day with variations, and this is at the pupil of the telescope, and that is what is corrected with the 80 centimeter M2 active mirror. And then during the day you might have different turbulent layers. So you might have you might have a high atmosphere turbulence layer. You might have 2 different layers, and they can even vary in height during the day. And this can be compensated by selectively making one of the mirrors from M3 to M6 active and compensate for the right layer in the atmosphere, or even a combination of the mirrors M3 to M6 can be used to compensate for the seeing. Yeah, all these things led to the effect that we had to upgrade also the science requirements document, and that is on the new version of that is now on archive. I provide here the link. And this new science requirement document, of course, takes into account all the advances we made with the telescope design, but also reflects the progress of the science since the first science requirement document, which was written in 2010. And it mainly concentrates also on the high polarimetric sensitivity of EST compared to DKIST. Yeah, just as an example, I want to show you one of these science cases here. Many of these science cases require this high polarimetric sensitivity. This is a science case which should observe the Handley effect and the scattering polarization. And here, polarimetric accuracy of 1.7 to 10 to the minus 5 is highly desirable. So these top-level science goals are summarized in this science requirement document. And the topics are very similar to what also DKIST will cover. But of course, the focus will be on different aspects, and the different aspects of mainly this high polarimetric sensitivity. The EST instruments are summarized here very early. The light will be distributed in an infrared station and in a visible station, and a lot of dichroic beam splitters will allow to feed the light into several instruments, narrowband images, broadband images in the visible and infrared. But what I want to highlight is that we also have the possibility to do very novel instrumentation, and there I want to highlight a development we had now recently made in our house. So what we want to observe on the sun are multidimensional structures. So they have multi-dimensions in space, but also in wavelength, and I symbolize that here with this banana. It can be a granule, a penumbra, or a filament. And if you want to observe that with a 2-dimensional detector, you can either slice in the wavelength direction, or you can slice in the spatial direction. But no matter how you slice, if you have a 3-dimensional object, it will in the end be very flat. And you can still recognize what it is, but you lose a lot of detail. And the advance we made at MPS is that we try to concentrate at these hyperspectral imagers. And a prototype of that is now running. The idea behind that is very simple. You have a solar image, and now you put small micro lenses to sample the image onto some pinhole array, which serves as the entrance of a spectrograph. You tilt this pinhole array slightly, you truncate the wavelength range using a narrow pre-filter to avoid overlap, and then on the 2-dimensional detector, you will get for every pixel of this pinhole array, you will get a full spectrum. And that this works was demonstrated with the MyHigh instrument developed by Michael van Noort at the SST. And such type of instruments will be key for the EST telescope. Here, test observation, using an iron line, and you see that this is this two-dimensional field of view. We can now make such an image. This is in the line core. We can make these images now for every wavelength because we have information of all pixels and all wavelengths for all time simultaneously. How important such a hyperspectral imager is even more seen when you observe a chromospheric line. Here, this is the same for the H-alpha line. You have here the field of view of the Maya instrument, two images showing the continuum, the slit show image and the reconstructed image from the spectrograph observations. The necessity of these field units is demonstrated here. How you see these are images in 1.3 second cadence, and you see how fast things evolve, how fast the spectrum of the H-alpha line develops, and it's very important to measure really in high time cadence. Very quickly about the status and the timeline. The EST came onto the European roadmap in 2016, and that was we are in the so-called preparatory phase, and there was a step back. So there was in 2019 a negative decision from the national governments, so it didn't go onto the German national roadmap, for example. But this negative decision triggered a new momentum in the EST team, and there were now the goal is now that we can replace the national funding by funding on the instrument level. So, for example, Germany will provide instrumentation to the EST on the instrument on a institutional funding basis, and so we are optimistic that this decision of the government will not influence the construction phase, or that the EST will become reality. So it led to the consolidation of the SRD. We will found a legal entity to manage EST, and to summarize, the costs for the construction and the preparatory phase will amount to 200 million euros, and the consolidation of the funding with the EU shall happen still in this year, so that in 2021 or latest 2022 the construction can start. The last slide, I want to show you that the site selection was already done. It will be on La Palma. The application for the construction site is done. The exact location is still under discussion. So here you see the telescopes, and this is already the EST. If you open a dome and you see the neighboring telescopes, DOT, the William Herschel telescope, SST, the Isaac Newton telescope. Where exactly it will be is still under discussion, because we do not want to interfere with the William Herschel telescope. They are a bit afraid that the EST will influence the seeing in the nighttime observatory. That is just who is then doing EST. It's a task of the European Association for Solar Telescopes, and it brings together research groups from 18 different countries, and the names behind the EST projects are mentioned here. The EST coordinator, Manolo Collados. Mats Karlsson is the East president. The chair of the science advisory group is Rolf Schlichenmeier at the Kiepenheuer Leibniz Institute in Freiburg. That was it. Thank you.
Thank you. We are already running behind the time, so I'm afraid we may not take many questions, perhaps one. Okay, then we can continue the discussion during lunchtime. And then I will hand over to Ayumi Asai for the public outreach session.
Thank you very much. My name is Ayumi Asai, the chair of the session 7 public outreach session. I'm very honored to be able to chair this special, unique, and the very last session of the APS-BM5. This session consists of 2 invited talks and 1 very short talk. So shall we start? The first invited talk is by Yaji-san, Kentaro Yaji.
Okay. And audio cable. Audio. Pointer. Thank you, Chair. Good afternoon, everybody. My name is Kentaro Yaji from Japan, National Institute for Fusion Science. I have a great pleasure to invite me this solar meeting. When I received the offer, invited talk, it's surprising to me. My talk title is Communicating Solar Astronomy in Hinode Era. In my career, I studied solar physics and solar flares. Firstly, I was working on public observatory and private university for a science education program. Coming to nowadays for solar observation duty and public relation and data archive. Now NIFS for public relations. For a long time, at the same time, I have the education and public activity with solar observation data. I report our activity about outreach, Communicating Astronomy Conference, what is called CAP. Sometimes I have presentations. This picture shows my presentation in 2010 at Cape Town. In such way, I report solar outreach with Hinode data. And when I attend the CAP 2013, Warsaw in Poland, Canadian astronomer comment on Twitter, Dennis Crabtree, Kentaro Yaji on communicating solar astronomy. I see. My talk is communicating solar astronomy. But since then, I am pleased with this phrase. I use it. In my contents today, I introduce EPO background in Japan, and I report some case power Hinode with Hinode and classroom activities. And I comment Hinode 10th anniversary event and summary. This is repeated shows my presentation CAP 2010 at Cape Town. This way, I report the outreach activity of the Hinode data. Before then, I introduce for short my current status. I am working on National Institute for Fusion Science, in short NIFS, for public relation and outreach. This map shows the central area of Japan. This is Tokyo, and this is Osaka. Nagoya City between Tokyo and Osaka. The natural NIFS is located in Toki City. This is 40 minutes railway from Nagoya. This is a research building and experiment building. In this experiment building, the large helical device, in short LHD. With LHDs, we achieved 2 years ago 120 million high temperature plasma. In such way, we are heading for realized fusion energies. Of course, for understanding fusion science, we are promoting public relation and outreach NIFS. For example, the open house. This is mascot character, Herika-chan, and this is Herika. And delivery experiment and classroom, and visitor guide, and public talks, and magazine for public relations. This picture shows education public activities since Hinode launch. As you know, 2006 Hinode launch. After that, to the public, interesting event or solar phenomena. For example, 2009, solar eclipse occurred. And 2012, annual eclipse and Venus transit. These pictures by Hinode X30 and
Hinode SOT. After that, 2040, as you know, big sunspot appeared. Amateur astronomers paying attention to the big sunspot and related. And after that, 2017, the big solar flares, a few X-class flares. Then many mass media asked our teams and report with effort. And 2016, the Hinode coming 10th anniversary, and 2017, now the ground-based observation, 100 years for observation. This image is calcium K images 100 years ago taken. And our outreach activities, 2007, Pau Hinode, later I detailed report start. And a joint observation campaign with Hinode start 2010. By the way, why communicating sun? Why communicating the sun? Yeah, of course, you have already your own answers. Well, for example, because the public have an intense interest on solar activities. Sometimes someone asks me, how about the sun? How many sunspot numbers? So, of course, because you want to talk about your own research results. Well, today talk conscious of these questions. How do you communicate the sun? Various ways. Typical way is talk and writing in other product publishing, experiment, picture book, craft, puzzle and quiz, workshops, social media, song, book, drama, toy models, digital data. For example, in Nowadays, produced goods, leaflet, brochure, papercraft, to clear file, DVD, papercraft, leaflet and brochures. Especially this papercraft is we called Pata Cube. This is produced by Tonoka-san, at that day public relations officers. And this picture shows the one scene of open house of Nowadays. This is an exhibition of Hinode pictures. Hinode team member recommend one pictures by Hinode, and visitor audience vote favorite pictures. Then this image gets #1 votes. Understand? Venus transit. And this kids play the Pata Cube large versions. And many books are publishing. And this is Shibata-san produced the solar photo albums. And Tsuneto-san writing, now the directors. And Shibata-san, Kamide-san, this is also Shibata-san, Tsuneto-san, last year Hanaoka-san, and Miyahara-san. I also one book writing. Title is The Book for Understanding Mystery of the Sun to the Earth. But I don't write almost the Earth. And you get my book, 1 Japanese yen, at Amazon booklet store, outlet store. In Japan, the for education public outreach background. First, Zan-san surely study in science class of formal education. For example, it is a textbook for science class in junior high schools. Junior high school students in such way that study the sun. This is solar structures and the prominence, solar corona, solar eclipse. Right page shows up as a sunspot and the solar rotations. Second, extracurricular activities of nature science as natural science in high and junior high school. Later, I reported the Let's Look at the Sun with Hinode. Third, there are many science museums, planetarium, and public observatories. This is also a report working group for public use of Hinode data. In Japan, there are 350 planetariums and 260 public observatories. Within astronomical facilities with solar telescope more than 50. But solar map shows the astronomical facilities with solar telescope. For example, the Fourth Science Museum and the Gunma Observatory, Kawaguchi Science Museum, Nagoya City Science Museum. Nagoya City Science Museum, inside the museum, the 2-meter live projection. So audience inside a museum, the observation of the sun. Last, fourth, amateur astronomers have high activities. I introduced one example, solar eclipse information centers. A solar eclipse information center established in 1977. This is a group of citizens like love and long solar eclipse. This way, they have solar eclipse report meetings. Before every eclipse, these meetings are held for exchange solar eclipse observation information. For example, the information work preparation and after eclipse observation report. Sometimes the researchers have a plenary talk. I also talk about the solar activities. As other topic, I pick up Kamogawa project. Kamogawa is a river name of Kyoto. The citizens try to measure the size of the sun from the limited line with the chance of the annular eclipse in 2012. Close up, I report to the working group for public use of Hino data. It is called Power Hino data. Well, Hino data is very important, not only investigating solar phenomena, but also giving new knowledge about the sun to the public and the educational communities. But researchers want to communicate observation results to the public, but very easy, and for research and operation other works. In addition, low budget and no powers. And educators want to use new observation results for planetarium, exhibition, and educational materials, and communicate that to the public. So 13 years ago, nowadays, that days, Hino science data have a collaboration with public use of Hino data working group. This working group is member of the Science Museum, Public Observatory, Planetarium, and researchers. Power Hino working group produced 2 DVDs. First DVD, the sun capture title is the sun capture by Hinode. Second DVD title is Approach to Solar Mysteries. First DVD is released in 2008, and mainly for educators to communicate to Hinode data to the public. This is consist of video part and a long part, and a short movie and a long movie. This DVD introduced initial observation results by Hinode, and containing a quiz regarding eclipse and Mercury transit. And full high definition movies are contained. Later, English version is released. Second DVD is released in 2009 spring. Produced by efficient use of exhibition of the Planetarium Museum. 4 movies concept, one of them is for kids. Distributed to junior high school and elementary school for 42,000 in Japan as an enclosure of science magazines. And now uploaded to YouTube Story Voice in Japanese. Introduce the first movies. Sorry, no sounds. Skipped.
Shit.
Sorry. よいしょと。
Below and to the right,
First,
the Earth can be seen.
13 years ago, we our working group produced these DVDs.
Hinode's solar optical telescope.
No. sorry. Okay, skipped. And DVD approach to solar mystery for video movies. This is consist of the 4 movies, 5 minutes. Especially this is for kids movies. Sorry, audio voice in Japanese. This way, dolphin and seagull have their health out of order. If this causes the sound, so seagull and dolphins are out of the earth to the space. File is heavy. Okay. This way, sunspot and flare movies played. Then after that, sorry. From this movie, we are developing the picture book with collaboration in JAXA ISAS. As the same the movies, the seagull and dolphin and Hinode-kun explain the sunspot and the solar flares. Then after that, this is I play picture story show at kindergarten, 2013. Disaster by tsunami and earthquake. A restaurant from Park Hinode. Park Hinode working group is quite unique activities, expanding DVD production to other diverse activities such as picture book. It is very important to collaborate with astronomical education facilities such as the Science Museum, planetariums, public observatories. It is the budget supported by NOJ, not only, but also we required as a grant by ourselves. This is contribution to report on Hinode mission extensions. Our next topic, let's look at the sun with Hinode together. It is a joint observation campaign simultaneously with high school and public observatory, museum and Hino satellite with Hinode. This is a EPO campaign. This is submitted as HOP 173 observation proposal, EPO campaign observation mainly for high school students. High school students who have solar observations interested in Hinode observation data, which promoting that they compare their own data with Hinode data. So far, for 10 years, 29 schools and facilities take part in. This overview with Hinode, shortly with Hinode, history since 2010. This mission is start of 2010. After that, at the solar maximum, at first, only 5 schools and facilities start. After that, solar maximum 2013, 12 school facilities take part in. After that, a new participant appears. In 2015, the high school students have a presentation, a junior session, annual astronomical meeting. At last, 2016, high school observed solar flare in success. This is timeline of solar observation with Hinode. For example, in case of joint observation in late July, till June 4th, we submit observation proposal to Hinode. Late June adopted. We have the solar joint observation late July. Then we form the participant the observation time. Usually in July and August, and 2 weeks. Sometimes we have previous lecture in participant schools. During observation, we determine observing region and request to Hinode site, reflecting the student request. The participant school have observation and study the data and have presentations. I also, after observation, the questionnaire survey and advice of analysis to the student, have a presentation various meetings. Sorry, tiny character tables. This table shows participant school facilities and observation years. Red light color shows the high school and junior high school. Blue shows the public observatory and museum. And orange shows the university, well, especially university astronomical club. This way, the table shows the solar maximum. Many schools and facilities attend these joint observations. This is a variety of school facilities from east to the west. This picture shows the high school student observation. Okay. Talk is 5 minutes. Okay. This is a sample of the observation solar images. Upper image is taken by high school student. Takasaki High School, Toho High School, and Uramanishi High School in HR images. Lower images are now the white light. This time the no sunspot, but after that some sunspot appeared. This is the XRT and the SOT calcium HLI movies. And July 25, the prominence observations. Prominence observation is very difficult. It is difficult to predict before, a few years ago, observations. But on that day, Hiroshima Johoku High School and Uranishiki High School, in such way, observation prominence. Also succeed the prominence, captures prominence, calcium H line. And the next day, another Tsuno High School change feature of prominence. This Tsuno High School have a presentation this way. This is Hinode XRT data, Mitaka white light data, H-alpha data, and their own Tsuno High School observation data. They compare their own H-alpha images with Hinode data and studied the relation between prominence and corona. They have a presentation in cultural festival prefectures. The students in such way have a presentation here. This way have a presentation, junior session in astronomical annual meetings. Especially the Uranishiki High School has a success observing solar flare and have a presentation report. Response by researchers. Since with Hinode start, foreign researchers have strong interest on the joint observations. They say good proposal. In Hinode science meetings, they ask me what's observation result. So circulating their solar image to Hinode researchers, they are always very delighted. That has also contributed to mission extension of Hinode. This image shows the solar flare observed by Uranishiki High School. Why the joint observation go well? I read the second items. Because Hinode observation data is more accessible to the student compared with other solar data. With Hinode have spread to other school and astronomical facilities and has interest in public. Lesson learned. 10 years since 2010 joint observation campaign, let's look at the sun with Hinode continues. Nearly 30 schools, facilities participate and have opportunities, access, compare with Hinode data and their own data. The students study science through the data, have presentations. Many researchers have intense interest and encourage the student. We have to give opportunities contact with solar data to the young scientists of public schools. Break. What is this? Toys and block. This is Hinode. But on the package, we cannot find the Hinode name. Orbiting Solar Observatory. But it is Hinode. Hinode 10th anniversary event 2016. This time, the Naoko Inoue, PR officer, is a great work and contributions. And she making a special short movie and planning the memorial public lecture after Hinode 10th science meeting. And interview with researchers. This is Shimizu-san, this is Inoue-san. And news, Naogen News special issues. She developing the polarization worksheet for education. Then we published the first 10 years of Hinode solar orbit observatories. Chapter 23, public outreach and education activities solar mission Hinode in Japan. I and Tonoka-san, Inoue-san is authors, outreach key persons. Shortly, I report the classroom activities. 10 years ago, I have a class, junior high school class. And lecture was the sun, solar structure and the solar numbers. And outside solar observation, prominent sunspot. And this with analyst softwares, they have a practice with PC, with fixed data. After classroom, the questionnaire survey, what are you impressed? And sunspot observation, prominence observation, operating software, they are interested in the topics. And I use this is hands-on work I frequently practice anywhere. Let's search granulations. Students search for kind of granulation pattern in limited times. This is original of the open house by Katsukawa-san. The student work and play like game. This is this very busy, very easy, and very difficult site. The students experience like researchers. Okay, in futures, it would be important to collaborate with astronomical education facilities, public schools. Now and in future, the next new solar mission, Sunrise, ALMA, PSP, Solar Orbiter, Aditya 1, Deepest Solar Sea appeared. Then we desire for public outreach, new idea, new activity, new method, new media, and new human resource. Especially the citizen astronomy is a very important keyword. Other big data, VR, live streams, STEAM, interactive, AI, and so on. Last summary. Hinode and other solar data are widely used for education and outreach in various ways and at various scenes. Many astronomical educators contribute outreach activities. Because many solar missions stand up in futures, we desire new idea and new human resource for outreach activities. Once again, why communicator sound? Finally, thank you for all people, encouragement, and contributions. Especially, I devote to my supervisor, my talk, late Takeo Kosugi. That's all, thank you.
Thank you, Yaji-san. Okay, now it's time for questions and comments.
Okay, first of all, thank you for this nice presentation about Hinode results. And I would just like to make one comment. So with my very limited experience of public outreach, I think a few years ago I decided to write a popular science book on the sun. And it was published by Oxford University Press, as you know. And to my great surprise, it was reprinted 4 times in 4 years, showing that there is a demand for this sort of activities. And on the basis of that, I would like to make one comment that I think we solar physics community can learn quite a bit from the cosmology community and particle physics community, how they do the outreach. I think those communities have been much, much more successful than our community in public outreach. So in solar physics, I often found that we have just last few years from various missions, we have got spectacular picture, and sometimes we just show these pictures and general public think that solar physics means just looking at nice pictures. Whereas cosmology and particle physics communities, they have portrayed their fields as a great intellectual adventure who answer some frontier questions of physics. So in my book, I tried to do that, and I would like to make an appeal to solar physics community that when you do public outreach, don't give the impression that solar physics means just looking at pretty picture. You should also try to portray our field as a kind of intellectual adventure, and sometimes talking about historical development and how it is connected with other things in science, other developments in science. Often that is helpful. That is my own opinion.
Thank you very much. it is important to interact with the other astronomical field. Now, Japanese solar educational communities are very active. Now, we collaborate with the researchers and the educators, not only solar physics, but also other fields, astronomical teaching materials. And I don't talk about that today. I have the Science Live Show Universe every month in the Science Museum that collaborate with other field researchers, give a talk to the public. In Japan, the various practices progress.
Okay, one more short comment, please.
Yaji-san, thank you very much. Very nice talk.
Thank you.
And I have a short reply comment to Chowdhury-san. You said the cosmology and particle physics group are doing outreach very well, but that is not correct, especially in Japan. Astronomical outreach is doing a much better job than cosmologists and particle physicists. Only in books, many books on cosmology or particle physics may be sold, but actually in popular science citizens, astronomy, including the sun, of course, because sunspot observation is very easy for children. Very, very popular, and the people are doing very well in Japan. And I think even in the world, amateur astronomy is very popular and doing a very job for many years. So please understand that.
Okay, sorry, time is over, so thanks again.
Thank you.
Okay, the next invited talk is by Helen Mason. The title is Solar Science Outreach in the UK and India.
Thank you. Can you hear me? Yeah, everybody asleep? I'm not sure if it's a great honor or a punishment to give the last talk in the conference. But anyway, I'm here. And I am pleased, and I thank the organizers for giving me this opportunity. Normally, I talk about science. I'm a solar scientist. I've worked on many solar space projects, from Skylab, Solar Maximum Mission, Hinode, SOHO, and more recently, ARIS and other things. But today I want to share with you some of the outreach. I tend to disagree as well with what you said. In the UK, we do a lot of outreach related to the sun, many different groups. And it's important. Why is it important? Our government believes it's important to inspire younger people. First of all, to give role models to younger researchers, but also to inspire students, school students, to take an interest in science and technology. So they encourage this, and they fund us to do this. So I'd like to share with you. Now, this is a personal perspective. I'm afraid I have limited time, so I'm really going to talk a little bit about the research I've been doing in the UK, the outreach I've been doing in the UK, the work in particular with schools more recently, And the broad title of Outreach in India was just a little bit too broad for me, so I've narrowed that down to the work that is going on here at IUCA SciPop and some of the involvement I've had with that. I do appreciate there is a lot of work in many other solar groups within India and also within the UK. So we are lucky in our field because basically anyone of any age can relate to the sun. Of course, they relate in different ways. And it's important when you're addressing a school or an audience to target that work that you're doing to the particular knowledge of the group you're addressing. But in addition, we do have the opportunity, both with the fantastic observations we've seen here, but also the fantastic theory as well now, to connect, and people are interested. They're very interested in the sun, they're interested in the observations. There's a great interest this week in DKIST and in the launch of Solar Orbiter. So we have an opportunity to engage, to link, and to explore this further. Over the past 20 years or so, it's been a golden age of solar space observations. I've been very fortunate with the members of my group to engage personally in the analysis of much of this data, from SOHO, TRACE, RESI, hard X-rays, Hinode, Stereo, SDO, IRIS, Parker Solar Probe, Solar Orbiter, and the upcoming Aditya L1. We have such a wealth, and the radio and the ground-based as well. We have such a wealth of information. And people sometimes think the sun is a little boring, but when you start to engage and to show them and talk to them about the sun, they soon realize actually it's not very boring. It's actually a physics laboratory that we have here on our doorsteps. So I'm going to start with a SOHO. I was part of the UK team for SOHO, the Coronal Diagnostic Spectrometer, and it was a wonderful opportunity. NASA is excellent at providing resources, etc., to engage with the public. I'm not going to go into the details of the science we carried out, but of course we looked at the surface of the sun, UV observations, and CMEs, all the things we've been discussing here. But in addition to that, NASA provided an exhibition. It's called Sun as Art. And it went around the country, and with it, explanations about what people were seeing. So these are real images, real observations from SOHO, and of course they've been manipulated a little bit, but actually provide a starting point for people to engage. Now at that time we had a solar eclipse in 1999 in the UK, went right across Europe. Some of you here might have seen it. We were very fortunate. I was fortunate to actually see it in the Channel Islands, one of the few places in the UK that we actually observed it. Now for that eclipse, we brought together a project which was originally called Sunblock 99, and we developed that into a project called SunTrek, which was a website. Now the interesting thing about this website that it was written by many of the young solar researchers throughout the UK. Of course, those researchers have now developed into professors and senior members in the groups they were. But they contributed, and we had classroom projects, and we had various activities, information about SOHO, and it was, the usage was immense, not just in the UK, but throughout the world. So it was inspired by SOHO, and it was inspired by the 1999 eclipse and the need to interact and provide information. So the sun is an inspiration for creative projects also. And what we've been endeavoring to do more recently is to link science and the arts. Too often they're separated and put into different categories, but actually life isn't really like that, and actually science and the arts are a unity and have been in the past and should be now. So coming to more recent project that I've been leading is called Sun, Space and Art. Now this came about as a result of a project that I work with, interacting very closely with the schools, with the International Space Station. We had an ESA UK astronaut, Tim Peake, who was up in space for 6 months, and our government put quite a lot of money into actually developing projects which would enable us to interact with school children of all ages, lots of different projects. Again, as I say, the aim of this was to ignite the interest of the young school children in science, engineering, technology. And they also realized that attitudes can be formed at quite an early age. So not only were they targeting the older children, which of course they can do lots of different projects with the older children, but they were also targeting the younger children. Younger children, 8, 9, 10-year-olds, are often very excited about space, about science, and harnessing that interest and bringing more people into it. So as a result of that project, which I worked on a project called Space to Earth, which I'm not going to go into the details of, but it was a challenge. It was bringing a physical challenge of covering the distance between Earth and the International Space Station in the school. And along with that, along with Tim Peake training up in space to run the marathon, we had connected activities, science activities that we run with the children. So my interest, of course, is in the sun, and the sun, of course, is very relevant to space travel. So we also, the space part is the effect of the sun, of radiation, of the solar wind in space and on astronauts in space. There we have a picture of one of the artists that I work with. It's a sundress, a giant goddess, sun goddess, and it's made out of smart materials. So we teach also the children about smart materials, different materials that are used, for example, to build these spacesuits that the astronauts need. So the project that I run is with artists. I have a team of about 12 people working with me, some artists, some scientists, and we come together as equals to work in the schools. So we go into the schools and we inform the children or have an interaction about the science, whatever particular topic we're covering. Last year we did quite a lot on the moon landings, it being the 50th anniversary of the moon landings, but also the sun, its importance to the Earth, and effect on other planets, exoplanets. And then we run in a project in which the children express what they have learnt in an artistic way. Now, we've chosen visual arts, but of course this can be done in other ways, and we have worked with dance, with poetry, and other ways. And in expressing what they have learnt, it reinforces what they've learnt, but it also develops creativity. And the idea is to harness this creativity, to ignite their curiosity and to develop their creativity. The space industry and the industries today require people who think, we call it outside the box. If you just follow a path that is a path which is based on what everybody knew before, we've heard several occasions, even in this meeting, where even Parker, his work wasn't accepted because he wasn't following that path. The great scientists think outside the box. They don't necessarily follow the path that everybody else has followed. The project is funded by our Science Research Council, Science and Technologies Facilities Council, now part of UK Research Institute Innovations. So they funded this work, they fund the artists, they fund our work. This is Helen Schell, who I've worked with a lot. She's also trained as an ESRO space ambassador. So she's also working on moon projects and Mars projects and been to NASA. So it's just an example. All of the artists we work with are professional artists, but we need to engage them as consultants. Here's an example of a workshop we did, which was just about the solar system. So the children have made pictures of the solar system, but we also get them to write about the solar system, what they've learned, what they're doing. And we get feedback every time. This is just a child. Today I love the lesson because the science and art inspired me. And what we find is that the children grow in confidence, that they're actually very proud of what they've done and what they've achieved. and some children that might be traditionally a little quieter will come forward and shine. I like personally to introduce historic scientists as well. For example, Galileo and his sunspot. These are his actual sunspot drawings. And I did want to mention one other place that I visited in Udaipur, and we've heard about the Mars telescope. So it's an opportunity to introduce science and how we work, how a scientist thinks, what is science, and the work that we do. Of course, I can't go without mentioning Newton, who worked in Cambridge, and these are some examples from the IUCAA SciPop of science demonstrations or toys that they have developed, and I'll say just a little bit more about that. IUCAA SciPop, we're very rich here, we're very lucky to have IUCAA SciPop here. It runs many astronomy outreach activities. Samir, who's here, and Sonal, I'm not sure whether she's here, and others work very hard to work with the children to facilitate public lectures from scientists and engage in science festivals, vast numbers. I'm always surprised when they say, I'm giving a talk on Saturday, and Samir said, oh, it's just a small group. And I'm thinking, oh, what about 50 students? Oh, no, 500 or 300. The numbers here are immense. They're much greater than I'm used to. So workshops and training of teachers, and particularly successful are their science toys. So I have some pictures here of various activities, and I think related to the solar work, of course, they cover all astronomy, and I think that Samir is going to say a little bit more about the zero shadow day that they have. But there's Aditya featuring, and of course, an Aditya is coming up now. They have developed ways of observing the sun safely, very important to emphasize, particularly to children, that they must not look at the sun. So for the eclipse they had here recently, they have to find ways of projecting the sun safely. So some of the work we've been doing in the UK, with the children now, of course, technology is very important, iPads. I tend to use social media quite a lot to transmit what I'm doing, as some of you may have noticed. I think it's important to get that out because people are interested. But in the schools, the children were using the iPad to present an iBook, which had quizzes, which had different things, information, and they interviewed people. They interviewed the head of education at the UK Space Centre, for example, Space Agency. They did media days, doing reporting about a solar storm coming, putting together a report, and producing exhibitions. So they decide to put on an exhibition about the sun, they simulate an eclipse, or they have lots of different ideas and things that they do. So we also try to target children that we wouldn't normally reach. Science is quite rich in Cambridge, as you can imagine. So the children there, most of their parents would be working in the University of Science. It's quite rich in science. But if you go to some other towns which we work in, Blackpool, Leeds, Manchester, up in different areas down in Devon, even rural areas in Norfolk, the children may never have met a scientist. They don't have science in their communities. We work in Wales, where 3 generations have been unemployed. These children are not normally reached. So we've been trying very hard, and SDFC has been encouraging, to reach diverse audiences, children that wouldn't normally be reached and that wouldn't necessarily engage with science. In this particular instance, in the middle there, that young lady is deaf. We were actually working with a school for deaf children, and we did some science interactions, which the teachers helped us to target the right level, and then we made some mobiles afterwards with the children. Again, very proud of what they can achieve. And the teacher said everyone was able to learn about the science and art together. No one was left out. Everybody in the class engaged. I just put up a thing there. We need to link it. If we want to target the schools, we need to link it to their curriculum as well to make sure it's relevant or it's an extension, so that we So I work very closely with teachers. I go to teachers' conferences, and I get to know the teachers so that I know, I'm targeting it at the right level. This is an exhibition put on at another school. These are quite young children, maybe 9, 10-year-olds. They had an exhibition. They brought their parents in. They each stood and they talked about different aspects of the sun, sunspots, different things like that to the parents and the people that came in. And they put on an exhibition about the sun. The future is solar. The science and learning was fantastic, and gave great context to the art that followed and linked in very well with the curriculum. That's the comments by one of the teachers. This is another exhibition in Wales. We work a lot with the museums, the science museums, but this is the Botanical Gardens, the National Botanical Gardens in Wales. We try to go out to different places that are not necessarily science-based, but we have worked a lot with the science museums and the science centres. But this is the Botanical Gardens of Wales, and the children all come together for something called the Great Science Share, where they all bring in the science, and these children had been working on art, expressing CMEs and all sorts of different things that they have there. So we have a very good team working over in Wales. Of course, as we've heard, the sun interacts with the Earth's environment, and the younger children even have heard about the Northern Lights, and they're interested to know that the sun is the cause of these Northern Lights, and it's an opportunity to learn more about magnetic fields, about the interaction of just exactly what we've been talking about, the source and the sun, the solar wind, and its interaction with the Earth. Of course, we know that has consequences, and society as a whole is very concerned about space weather effects, and we need to be able to communicate them in a practical and a real way. In the UK, it's number 4 on the UK's risk register for economic damage. So it's of great concern. We get feedback, and sometimes we get so much feedback, it's a little bit overwhelming, so we put it in a form like this. This is just one event that we had in a school. But obviously, we ask them at the end what they've learnt, what they liked about it, how they would change it, and we get feedback in that way from them. With the work with IUCA, I'm very, very happy to have worked so many times with IUCA. I visit Dergish's group quite frequently, every year, I think. I make an annual trip here. Dergish, of course, originally, after being at Max Planck, worked in Cambridge as a postdoc for many years, and then came to IUCA, and it's a great honor for me to come here and work. Sargam, who you see sitting next to him, was from IUCA and came and did a PhD with me in Cambridge, and has now finished, and now is, after a short spell back in IUCA, she's now got a postdoc up in Glasgow. And it's great to interact with the young researchers here, and more widely with some of the colleges, going out to ISA and Ferguson College. It's a great pleasure for me to do that. But we've also been working with the schools, and IUCA SciPop has facilitated visits to the schools and the school children coming in. There we're showing them, I think, a projection of the sun, and we've worked in other ways. And one thing that we have been developing, and we need to work on a little bit more, is a project called Surya, Here Comes the Sun. And we had some young university students working on that, producing lots of materials, PowerPoints, and games, etc., information about the sun, and leading these young people were actually leading workshops with teachers and with students. So it gives, when you can engage young people, as I try to engage young research in our activities too, it gives them an opportunity to develop their skills too. So it's not just us, we get the help, but we also enable them to develop their skills. So, as I said, we provide support for teachers, we're providing resources that teachers can use, and this is an example of workshop here at IUCA for teachers, but also in the UK. We run specific, we call it continued professional development for teachers, so that they can then use the resources we've provided, the information we've provided in their schools and further afield. This is just a comment back from one of the teachers who attended one of these sessions. We asked, what do you feel that your students could gain from a sun, space, art, science, art session? And it doesn't have to be sun and space and art. It could be other areas of science. And the teacher said creativity, independence, ownership of learning, which are great things for the students to learn and engage with. Astronomy societies, we've heard earlier, they're great for interacting with and promoting areas of our field. This is the local astronomy society here in Pune, and they had an exhibition about Aditya, about solar science, and provided models and all sorts of innovative things. So it's great to harness their enthusiasm, their ideas, their energy. I'm not alone in the UK, as I say. Northumbria does a lot of outreach. Lots of places in the UK do a lot of solar outreach. And this is something that Robert Walsh at UCLan, University of Central Lancashire, did up in Blackpool. You can see down the bottom, if you look carefully, you can see the people down the bottom there. This is a big sun, and it has real data from SDO projected onto it, and it changes and revolves. Absolutely stunning. It was in a big, dark ballroom, and he's had it in several other places, and we bring in the school children. So I worked with him on this, and we ran projects with the schools, with an artist, with Helen Schell, to develop the information that the children had learned and what they knew about the sun. He also had information boards, and we talked to them. Great success. So the future is great. The past has been great, and the future is great. I'm very excited about solar physics. I love passionately solar physics, and I love to share that excitement with other people. I'm very excited to be here at this meeting. So we've heard lots of talks about Parker Solar Probe. It was amazing, the talk we heard about that. And Solar Orbiter, hopefully soon, will be launched on Sunday. It will give us new results. And of course, these are just the space projects, but Aditya, possibly 2021, and the involvement here of the group in the SUIT instrument being led by Dergish and his group. So we have a very exciting, and possibly Solar Sea we heard about, and of all the ground-based, I haven't covered nearly anything, all of it. We have a lot of exciting projects. So how can we give opportunities for the young solar researchers to engage? We can engage them, if possible, in the projects that we run, in open days and foundation days, astronomy clubs, science festivals, and we can give them the opportunity to give public talks. And here's Avatana giving a public talk here at IUCA. It's a training opportunity for them to be able to communicate what they're doing. Social media, and of course they have their own ideas as well. They may want to use much more, IT, we've heard of data, these things that those of us that are getting a little older aren't so familiar, isn't so easy to us, but they're fresh and they're new. Virtual reality. We have some virtual, Miho in Paris does a lot of virtual reality, CMEs and things like that. So my message to you is to get involved. If you can, as a young researcher, it helps you. It helps your training, it helps your communicator. So getting involved. So life is like a camera. This is from one of the schools that I visit here in India. Life is like a camera. Focus on what's important. Capture the good times. Develop from the negatives. And if things don't work out, take another shot. I just love that because it looked a little bit like one of our satellites. So thank you. Thank you very much.
Thank you very much, Mason-san, for the wonderful talk. Now it's time for questions and comment.
Hi. So the science outreach programs are typically a week or maybe 10 days long, excitement and fun. So how do you think it can be carried forward to classroom teaching, and how important is it? What's your comments on that?
Could you just repeat the last bit?
So, I mean, how can it be carried forward to regular classroom teachings? How important is it, and what are your comments on that?
To bring it forward into regular class teaching?
Yeah.
Yes, I think that it's important in the sense, to be at conferences and to be represented. But when they have summer schools, I think it's important to be incorporated there. But opportunities maybe at the institutes or the places where you work. If there are groups, I think it's important to come together and to, I know in ISA and in Ferguson College they have astronomy groups, but they do things as well in that regard. So in the formal teaching, it probably doesn't necessarily come into the formal teaching, but I'm at the Department of Applied Maths and Theoretical Physics in Cambridge, and we have something there called the Millennium Maths Project, and that I've worked with them in video conferencing, various things, and they positively encourage the students to engage with that project, to go out to schools and to do various things that are connected with that project. It's difficult when you're young to lead a project because it probably takes quite a lot of time. But actually, if we who are leading projects and in the different places can think of ways to engage younger people, I think that when I go out to like I was in Blackpool, there were quite a few younger people there, and particularly the children relate very well. They don't necessarily relate that well to grey hair, but they relate very well to people who are younger and can talk to them directly on more of a level. How did you get to university? What did you study? What did you do? Why are you interested?
Any other comment, questions?
I'm pleased to see so many young people at this conference also. And can I say, because I know the awards ceremony is coming up soon, do you want to plug yours in? Can I say I'm very impressed by the quality of the posters and the talks everybody has given, but in particular that the young people have given. So well done, everybody.
Okay, thank you very much. I have one question. Either you or Yaji-san. I think real experience is very important. You are collaborating with art, and Yaji-san is using data, observational data as educational material. But I think it's also important to do the real experience. Use some telescope or know how to work the instrument.
Yeah, I think that there are some public communicators that perhaps are not scientists, but I think it's important, if that's the case, to work closely with the scientists. I was very impressed by the previous talk, and I think there may be an opportunity for us to work more closely. I mean, I've worked on Hinode, but I haven't used any of the Hinode resources, and perhaps that's probably because they're in Japanese, some of them, but the ones that are in English, I think there's perhaps an opportunity for us to share. I've worked closely with NASA, but I haven't worked so closely with my Japanese colleagues. I have worked with Indian colleagues, but I think that would be a good opportunity to do so.
Okay, sorry, time is over, so now thanks, Helen, again. And before I close the session, Samuel Durude-san have a short talk, 5 minutes talk.
Yes,
so
very
please.
short. So thank you to the organizers for allowing me this little talk about solar and maybe solar system outreach in the Asia Pacific region. It just came to me a few days back that there should be a discussion on how this particular group could go forward and contribute to their own region with the outreach resources they have. There's so many resources which have been reported just now. But one thing that I notice is that when we say Asia Pacific, there are a lot of countries and places. They're not all of them are listed here. But and this is the only map I could find without international boundaries, which we are always quarreling about. But science, astronomy unites us all, so that it should be beyond boundaries. So I want to propose a small activity, which could then have associated activities, which unites us all and makes us collaborate all across these countries in this region. And it is also another thing that I represent the IUCA Scientific Public Outreach Program, whose one of the key areas we work in is low cost and hands-on activities. So this is one of those. Quickly present to you the Zero Shadow Day activity, which this institute has initiated a long time back, and we've been doing a very successful run of these activities across the country, and a few other countries have also joined us in this region now, so we are growing. So shadow is a very beautiful thing, but sometimes the lack of a shadow can also be beautiful, and this is what we celebrate in that Zero Shadow Day. Well, zero shadow, and it's also useful if you remember Eratosthenes' experiment, which was done in a well, and that is that well in which he used the fact that there was no shadow on that day, but his friend somewhere else had a shadow, and that gave us the circumference of the Earth. So it can be useful. It's okay. Sorry. So this is that experiment, right? Now we can directly think of doing this, but this happened particularly on a day when the sun was overhead, right, at one place. So this is the place where the sun was overhead at Syene, and on that day at Alexandria it was not. And that led us, to think that the Earth should be curved, and so we still do that activity. I know many people who are doing these Eratosthenes experiments everywhere, right? Of course, in India, in general life, we don't sometimes realize that such an important thing is happening, right? Eratosthenes did such a calculation, but people are just playing cricket in this picture, which is a very favorite sport in our region, and they don't have shadows. Do you notice that? Amazing thing, and they're all busy playing, but they don't notice such an important event happening right then, at that time. So this is mostly during summers in India, and there should be 2 of these because of this region. Okay, so if you're a cylindrical object, you actually have a zero shadow when the sun is right above you. Otherwise, if you have appendages, you can have some shadows, but cylinders are the best. Okay. So what is zero shadow? A quick primer to that. You know that in this picture, if you are standing here and this is the North Pole, direction of the North Pole, the sun's path in the sky, okay, is from east to west, but it may not be right above your head. It's going on a particular declination line, and that line changes over the seasons. So this green would be the path on the what we call winter solstice. I know there are people from Australia here. So we call winter solstice. There's a shorter path for us. On the equinox days, it goes right from east to west on this line. And on the summer solstice, it takes a longer path, right? And in between one of these days, depending on your own latitude, and whether you are between the tropics or not, it does pass overhead. Now this is for the equator, which is definitely within the tropics. On the equinox day, the sun will pass right overhead. But on the other days, at noon, which we have this misconception that at noon the sun is overhead. And everyone you ask will tell you that in general, not in this room maybe. But so that we cannot always go out and tell people you have a misconception. We say let's celebrate the fact that it is not on the top every day, but on a particular day we have a reason to celebrate. So that is the day we celebrate. For the equator, it will be the equinox days, but for the other latitudes, there are days in between. And that is what we have proposed. And you see the tropics, if you see the area covered by the tropics, there's a lot of countries which can use this fact that they have zero shadow days. And you can see they also, so I can just zoom it in, maybe you can see your country here. There are 100 countries in the tropics. And these are the countries which are always referred to as underdeveloped or third world and things like that, right? Which do not have resources. We do not have resources to have, slideshows and exhibitions. No offense to anybody, but we try to find the least costly thing to do, right? So zero shadow day basically requires you only to have the sun shining overhead at local noon. That's all you need, and then it needs your imagination. So you just go out, find out which day is zero shadow day for us, right? And then do some activities around it. It could be, then you put in anything. You could do daytime astronomy activities, you could do your exhibition, you could do a road show, you could do a film show, you could do talks, whatever. But it's just that we are celebrating the special position of the sun on that day, right? It is a great outreach activity, and I'm showing you, again, Helen referred to our numbers, so we have no dearth. Again, a whole school celebrating their own, in their own way, the Zero Shadow Day. And you see, these are not activities that we have prescribed them to do, right? We just tell them there's a zero shadow. You know, you find out your own ways to celebrate it. You find out your own ways to tell students how to do it. These teachers found out a way that make them stand in a circle and they all look at their shadow. They did a lot of solar system outreach around it, because it's not just about the sun. You can't just talk about the sun without talking about the earth, without talking about the other these things. So teachers found it a very nice and inspiring and enabling event in India. We've been doing this at many places, and you can see this is some places. Ayuka has been doing some things, but at other places, schools and astronomy associations have taken it up. It's been a great outreach activity because it brings people out of the classrooms into the real world, actually look at the sun. We can talk all about the sun and universe inside the classroom on a blackboard or the projector, but this basically takes us out. So, this is not only for students. In many ways, people have put out fruits and vegetables on the road, saying let's look at their shadows. They've put out telescopes, and as I said, associated activities can be done. So this is a small report. I won't go into details of it, but we've been doing this activity as an organized one across the country, and we've had great success. We've had regional workshops, teacher trainings, large-scale public events as well. And what I'm proposing is that if anybody is interested, you may be researchers, but you may have friends in outreach in your countries, in your region. If you're interested, you can put them in touch with us. And we have created several resources so that at least you can find out what is the Zero Shadow Day. Sorry, I'll just go to the next one. So quickly. There's a website we've developed which has an online tool where if you go to the website, you click on your own place, and you'll know when your own Zero Shadow Day will happen. Right? This is of course showing India, but across the world, between these lines, you can click anywhere and get your own Zero Shadow Day date and time. So what I'm proposing is that if there's any interest, in carrying out these activities, you can access this website. This is ZSD, is the short form for Zero Shadow Day. This is an older link, but it still works. A lot of resources are there, and you can of course get in touch with us. That's it. Thank you.
Thank you very much. Thank you very much, Samir-san. So now time is over, so let's thank him.
Yes,
and
so I won't ask for it. This is my contact ID, but you are welcome to catch me. I can also share my cards with you. Thank you.
So let's thank all the speakers of the session. Thank you very much. Okay, let's move on to the award ceremony. Yeah, okay.
Maybe I should go up. Yeah, okay. You can set up by that time probably, yeah. Hello, okay. So thanks, Ayumi-san. So it's a pleasure for me to make these announcements. So the first one is for the best young oral presenters. So I must admit, this young definition was also that the students or postdocs up to 3 years from their PhD submission. So that was the condition of young. But I see the awardees are all PhD students. So they have beaten up the postdocs that way. So the first prize goes to Sanchita Paul from SESI, Kolkata, for her presentation on magnetic cloud flux erosion mediated by reconnection with ambient solar wind. She will get an online subscription for solar physics. So solar physics is an expensive journal, we all know. So I think those instructions will be given by Durgesh, or email will be given. That's right, that's right. I will just going to do that. So please have the certificates ready, and Mike on behalf of Solar Physics Journal and as a chief editor, yeah, will hand over the certificate to Shunchita. So the second prize goes to Lakshmi B. She's also incidentally from CSC Kolkata. So I think Dibyendu can be proud. Her presentation was on solar cycle variation of large-scale plasma flows, and she gets from the behalf of RAA the certificate. So you can do the honors, or no, I think Arnavda will do that. Yeah, I mean, yeah. So this is the research in astronomy and astrophysics, and from the editorial board, Professor Arnav Raychaudhuri will take the honors. Yes. And now comes the best poster award. So this was restricted to only PhD students, and we had good competition actually. Maybe because there was a cash prize in that. So that's a 5,000 cash award. I think Durgesh will, or if is Shomoka here? Okay. So for the closing remarks. So on behalf of Professor Raychaudhuri, Durgesh will do the honors. I have to still make the announcement. Who is the honor? So that goes to Zubair Sheikh. He's from Indian Institute of Geomagnetism for his poster comparative statistical study of characteristics of plasma in planar and non-planar ICME sheets during cycle 23 and 24. I also would like to actually really congratulate him because, as I think it was remarked earlier as well, when we were very young, the solar community and the heliophysics community was not talking to each other that much. And I'm very happy to see he's from IIG, which is a geomagnetism center, and he has participated very actively in the solar meeting and have won the best prize as well. So really, really well done. No TDS? Yeah, we had deducted tax in the source, so I was just joking. So that's called TDS. Okay, so that I think concludes the award ceremony, and I will request Durgesh for making some the next proceedings.
So the next speaker to announce the next Asia Pacific meeting is Professor Arnav Raychaudhuri. So just sign it and pass it on to me, okay? The talk is ready.
All good things come to an end. So we are coming to the end of this wonderful conference, and you may wonder, I think, what lies ahead. So I have been given this task of announcing the next APSPM. So as you all know, that one shortcoming of this meeting is that because of this very unfortunate coronavirus thing, our Chinese colleagues could not attend this conference, though some of them gave talks through Zoom. So if some of the Chinese colleagues were here, then I would not be standing here now. They would be making the announcement. But since they are not around, I have been given this opportunity because I had long association with Chinese solar physics community. I had been a visiting professor of Chinese Academy of Sciences for some time, and one of the Chinese associate member, Jie Jiang, did her PhD thesis under my supervision. So probably I have this, because of this connection, Durgesh requested me to make this announcement. But before announcing the and talking about the future, I thought that I shall just mention a little bit about the past of this APSPM, because many young people may not know about it. So I can mention that around 40 years ago, when I was doing my PhD at University of Chicago under the supervision of Professor Eugene Parker. So at that time, there was very little solar physics being done in the Asia-Pacific region. Of course, Japan is one country which had a long tradition of solar physics research, but outside Japan, almost no country in this region had a sizable solar physics community. So it gives me great pleasure to see that within my active research career, I have seen solar physics blossom in this region, and this may be the region where solar physics within the world where the solar physics is growing at such a fast rate. And till about 10 years ago, these solar physics communities in different Asia-Pacific countries were not interacting that much with each other. So we are all looking towards the West for appreciation, collaborations, visiting positions, etc. And then some of us felt that it's good to have some meetings where these communities, solar physics communities in these different countries can come together and may get to know each other. So here I have just flashed an email I wrote about 10 years ago, 24th May 2010, to several solar physics colleagues in this region. So it's a long email, so I am showing only the first part of it, and I can just read the first small paragraph. So some of us solar physicists in India have been wondering if it will be worthwhile to organize an Asia-Pacific meeting on solar physics. This is to share with you our ideas on this matter and to receive your feedback. So after receiving this very favorable feedback, we decided to, So we decided to have these APSPMs. So first one was held in Bangalore. And in fact, when I wrote that email, I did not propose a series of meetings. I thought that there would be just one meeting so that these various communities get to know each other. But after this first meeting was so successful, several meetings were held. Second one in Hangzhou, China. Third one in Seoul, Korea. Fourth one is Kyoto, Japan. And now after a cycle, we have again come back. This meeting is being held in India. So right now, only 4 countries in our region have sufficiently large solar physics communities to hold this meeting because it requires quite a lot of work. Unless the community is sufficiently large, it is difficult to organize this meeting. But I hope within the next few years, some other countries in our region also will have sizable solar physics communities and hold these meetings. So for the benefit of young participants, I shall mention one thing, that only for the first APSPM, we decided to bring out the proceedings, which were edited by me and Professor Dipankar Banerjee, and afterwards we did not bring out proceedings. And in these proceedings, there is a historical section where I think some of the leading scientists of different countries, India, China, Japan, Korea, Australia, Taiwan, they all gave a historical account of how solar physics developed in these countries. And this is available on the internet. Maybe I shall request Durgesh to send a link to all of you so that especially the young people may look at it, and for them it would be maybe of great interest to find out how the solar physics developed in our region. And then lastly, I should mention that this APSPM has no society, no office, no secretariat, no fund, no website. So basically, when an APSPM is organized, the organizers of the host country for a few months maintain an website for that particular APSPM. But otherwise, since we don't have a secretariat, we have not or maintained a regular website. So now that this meeting is becoming so important, and I believe that it will be worthwhile to have some sort of a website giving the basic information about the previous APSPMs, especially the names of the recipients of young participants in the previous APSPM, since some of them turned out to be very, I think, outstanding solar physicists as time went on. So some of us who started APSPM, we are now probably on past the peak of our career. So I would request some of the middle-aged scientists in these different Asia-Pacific countries to take an initiative to start a website or something like that and put the basic information about the past APSPMs, which it will still possible to get the information about the past APSPM, who are the invited speakers and who are the recipients of these young participant awards and things like that. And if we delay, it may be difficult to get that information. And I can mention that some of the past recipients of this young participant award gave talks in this particular APSPM. I think Yang Guo, Hesu Yang, Vidya Karok, Gopal Hajra, and I don't know if I have missed any other name, then my apologies. And one past recipient was a member of SOC, Jie Jiang. Okay, so with, and I also feel happy that several of them had been my PhD students, Jie Jiang, Vidya Karok, and Gopal Hajra. Okay, so now let us come to the 6th APSPM. So we are very happy that our Chinese colleagues have offered to hold the next APSPM, and they have sent us some slides about it. So it will be hosted by National Astronomical Observatory, Chinese Academy of Sciences, Beijing. And also I shall mention about the time. So in the business meeting of SOC, we also discussed how frequent these meetings will be. And also we kept in mind that in different countries, weather conditions may be different, different times of the year may be the best times to hold this meeting. So we do not want to be too rigid and decided to give sufficient freedom to the organizers of the APSPM. So we stipulated that the difference between two APSPMs should be more than 2 years and less than 3 years. With that restriction, I think it would be left to the organizers of the next APSPM when they want to hold it. So our Chinese colleagues would like to hold it in the autumn of 2022. And the main person who have volunteered to hold this meeting, to be the host of this meeting, is Professor Yihua Yan, a very distinguished solar radio astronomer. So many of you know, and in fact, you may know that he was for several years, he was the president of Division E, Sun and Heliosphere of the IAU, and at that time I was also a member of the executive committee of Division E. So I had the pleasure of working with him and know that he is a very responsible and very capable organizer. So I'm sure that he will do quite an outstanding job. So they still have not decided about the site of where it will be held. So one possibility is certainly the campus of this Chinese Academy of Sciences, which is in Beijing in a very convenient location, almost next to the ground where the Olympic Games were held a few years ago. And the other possibilities are this place, Muser, where there is a radio telescope, and another possibilities, Pingtang, this Guizhou region. So we, in the business meeting, we communicated to the Chinese colleagues that it is very important that young people from various countries should be able to attend this conference. So it is this time I find it a little bit unfortunate that though there are a large number of young people from students and postdocs from India are attending this conference. I think there are very few young participants from other countries. Of course, there is about half a dozen Chinese students who are supposed to come who could not come. So I would appeal to all the senior people of different countries to make sure that in future APSPMs, you please encourage your young students from your countries to come and also try to find out their financial support. So we pointed out to the Chinese colleagues. So it should be held in such a way that young people who have limited funding may come easily, and there should be not inexpensive accommodation. So the Chinese colleagues told us that they would look into these things, and then they will decide what will be the more appropriate place for this conference. Okay, so that's all I had to say, and now I shall give the microphone to Durgesh, who will make the last few concluding remarks and also thank his team who have been involved in organizing this meeting. But I know that Durgesh, being a very modest person, he will not thank himself. So let me take this opportunity of thanking him. I suppose you all agree that he did a fantastic job. So now Durgesh.
Thank you, Arnab. I thought I will thank myself as well, but anyways, you've done it. So, right. So I have had a lot of fun this week. I think I've lost a few kilos, but that's good. So to begin with, I mean, on behalf of SOC, LOC, and on behalf of all of you, I would like to thank our director, Professor Soumya Chaudhary, to give all the support possible for arranging this meeting. And IUCAA is a great place because we have a system in place where we have a team of people. Everything is done over email, and I'm lucky to have those people around. And I would like all the SOC, LOC people standing there, please come in here. And I would like all of you to give a big hand of applause to them. So without their help, this would not have happened. Actually, when Arnab approached me that should we do this, I was reluctant, but then I was confident that I have such excellent team, so we can easily get it going, and we can do this. Thank you very much. And one of the things which we had to consider to accommodate as many young people as possible, and almost without any cost. And Prasad came as a rescue, as a member of SOC. He's a co-chair with me, and also a LOC member, and taking all the responsibility, whatever is happening at ICER, accommodating people. So thank you, Prasad, and his team at ICER. A special thanks to our technical team for all the Zoom talks, I think, which worked perfectly. So Santosh Jagade is here. He just came around running timed perfectly. And all the speakers who, they're not here, but if the live stream is working, they probably can see it. They did perfectly good job, sitting midnight giving this talk. Nurdin Rofi, I had to call him, he said, wait, half an hour, I'm running to my office. And he did actually a nice job, so that was big thanks to them as well. a lot of things which you see on the web page and changing the programs and all that happened so quickly because of my students here. So Vishal, Abhishek, Avyarthana, Ashwanya, Srijit, so they all have been doing all the great things. I was just telling them what to do and probably forgetting many times they were telling me what to do as well. So backstage support during the award time. So a big thanks to Shivani. Is she here? She came, she timed her time as well so that she can bring all the awards for you. And one additional thing, when we were making these programs, we selected the speakers, we selected the chairs, but one important component is for running around with the microphones during the question answer session. So at the end, I requested Vishal to make a list of all the students coming from within the country, and we allocated them session-wise. And after that, we had no job to do. They were so responsible running with the mics, and we were just relieved. So can you all stand up? Thank you very much for doing that. That was a great help. And it's also a very special meeting for me because some of my mentors are here. Helen from Cambridge, Sarah from HAO, Julio, Mark, thank you all for coming from your very busy schedule. So I appreciate it. A big thank you to all. And a lot of people who could make it from Japan, from China, not from China, from Korea. It's unfortunate that only Mike could come from Australia. Alina and Paul had to cancel their participation. And I think there was some big news about the coronavirus. And it's unfortunate that our Chinese colleagues could not make it for the meeting. So thank you all for coming. And it's unfortunate that Chinese participants couldn't come, but they have been attending the meetings because on the live feed, we can see how many people have been connected. And we see that the number were going to 30 to 50, sometimes 90, 81. So a big, big thanks to them for sitting all the way through. Let me see. The other thing, yeah, I would like also to say a few words. I have wonderful colleagues at IUCA, so that has been a big support, particularly for me to grow in my career and also the solar physics community in the country. All the senior people, plus the people who are of our similar age. People are talking about 3Ds, so let's keep it going and let the solar physics grow probably even faster rate, as Arnabda was pointing out. So thank you all very much. And then at the end, I would like to thank you all for coming, despite my email that none of our colleagues can make it to the meeting, and then I get Marcel was the first one to say that, hey, I thought I was coming for the meeting. I said, oh, no, no, no. Then I replied that none of my Chinese colleagues are coming. I said, oh, I made a mistake, you know. So I had to actually then write the third email saying that none of our colleagues working in China could make it for the meeting. So thank you all very much for coming. And I will pass on the mic to, have I forgotten? Yes. See, they're reminding me, you know, they've been doing it from last 2 months. A big thanks to you. Can you please stand up during the live streaming? He has been sitting all through here. And Shashank for being here and taking all the pictures and putting into the media. And with that, I will pass on the mic to our director, Professor Somagraj Chaudhary, to say that the meeting is over. Thank you.
Toughest job to be handed the mic in front of such hungry people. Everybody's, and Arnav has already done my job. I said I wanted to just thank Durgesh for doing all of this. So again, I should. Thank you very much for coming. I won't keep you from lunch. We started with a big bang. Actually, a lot of you don't know that on Saturday, in order to build that place for you for lunch, they dug through the mains electrical cable for the whole of IUCA. And so we were without electricity for the whole day, for the sake of this conference. And so I hope nothing else goes wrong. And I think all through the week, we've had a wonderful time, and I'm glad you also enjoyed what we had for you in the evenings as well. And just looking at people interacting all across was wonderful. It is unfortunate that a large number of us couldn't come to this meeting because of what happened, but again, thank you very much, and I hope to see you all again in various capacities coming back to IUCAA. Thank you.
Hello. So apparently there is some special lunch for all the PhD students, the young cadet people. So we must have lunch on the other side of the pool, and the older people have the lunch on this side of the pool. Thank you.